Hello. Everybody ready? Welcome. I'm so glad to see you here. My name is Robin Bell. I'm a research professor here at Lamont, and it's my tremendous pleasure to welcome you here to our open house. Lamont's a magic place. What can I say? I came here as a graduate student 42 years ago, and I know, and it's such a magic science place that I'm still here. It's a place where you'll hear discoveries about the bottom of the ocean have been made, where we learned about climate and climate change, and we think about how to help our planet as we understand climate is changing and what we can do about it, while we continue to explore places that people have never been. So it's been here 75 years, which is pretty crazy. And I hope you enjoy it today. There's, everything from things that you can learn about how the planet works, ways you can learn about how to engage young children and adults in science. And if you like this lecture, we have more lectures, public lectures coming up, and you can sign up for them outside. There's one coming up in November. So now I've given you a little overview of Lamont, and I could talk about Lamont forever, but we want to hear from these three amazing women who you're going to hear from today. It's really remarkable having, over the decades I've been here, seeing the culture of science change. Just as a hint, when my class, when I arrived, there were no women on the faculty, and only 2 women in my class graduated. So just to see women in leadership positions and this changed culture heartens me to see that communities can change and we can get everybody to the table. Partially because, and what is really important is that our planet needs smart people thinking about it, and we need all smart people thinking about it. So that's why it's wonderful that we see such a more diverse set of faces around the table working on our planet. So with that, I'm going to introduce the 3 amazing women you're going to hear from today, just to give you an idea of how amazing. One was born on Wild Harbor, or grew up on Wild Harbor, right? Who could imagine that? Somebody came from the Dominican Republic, and the other person came from Madagascar, just to let you know how global science really is and how we're really trying to build that global science engine while we study the globe. So first, we're going to hear from one of my dear colleagues and dear friends, Vicki Ferrini, who I met on the Hudson River when we were working on a project many years ago, maybe 20-ish, mapping the Hudson River, where she had this amazing technology. I had not quite such amazing technology, where she'd bounce sound off the bottom of the river and image, sunken ships, Revolutionary War things, giant sand waves, oyster reefs, all this amazing stuff. Since then, she actually got her PhD out of the Hudson River work based on that mapping. And she worked at Woods Hole, and then we've been very lucky to have her back here at Lamont, where Vicki is a total leader, both in data, because data is what we as scientists hold dear. It's kind of like credit or your savings as a human being. When you think about money, data is like the thing we hold dear to us and what we have to take good care of. Vicki is currently is Associate Director for Diversity, Equity, and Inclusion. And out there you may have seen a project called Inspire, funded by the National Science Foundation, to really build a community of diverse people to work on science. And Vicki is the lead of that, and I have the honor of working with her. So if you think about data or you think about equity, that's Vicki. And with Vicki, we're really lucky to have 2 of these rising stars, Sheila Cáceres, sorry. Anyway, she's going to get it right, who is a research assistant working with Vicki on these projects where I bet you're going to learn how we don't really know what's the bottom of the ocean. You open Google Earth and you think you do, and you don't. That's a good estimate. So Sheila's originally from the Dominican Republic. She runs amazing programs in the Caribbean and Latin America, working again to get people to understand how to map the bottom of the ocean, share their data, and build this community project called Seabed 2030 that you're going to hear about. Tinah Martin is also a data manager in the bathymetry world that Vicki runs. And I liked there's all sorts of words here, but I like to think what Tinah does is she's in charge of the Indian Ocean and the coast of Africa. If you want to, there's all sorts of acronyms that go with that, but really the essence is that she is this key connector for people around that ocean basin to understand the importance of mapping the ocean floor, how to do it right, and how to share that data in a way that benefits everybody. So I think I'm going to stop there, and because they're way more interesting than me, and I think I'll let Vicki start. So please, let's welcome Vicki, Sheila, and Tinah.
Thank you, and thanks, Robin, for that introduction. It's a pleasure to be here with all of you today. Thank you for coming. We're going to talk a little bit about Lamont's contributions to seafloor mapping, past, present, and future. And I'm going to provide sort of the foundational introduction, and then Sheila and Tinah will tell you about some of the new things that we've been doing here in our group. So just to kick off, a few examples of why seabed mapping is important. I'm not going to read the list, it's pretty lengthy. But there are a huge variety of reasons that we need this kind of data, from basic understanding of the planet, the processes that shape the planet, what happens underwater, offshore infrastructure, resources, habitats, sustainable management of resources, safety of navigation, lots and lots of reasons. And it's really a foundational data set that remarkably is very sparse in terms of its extent. So when you think about the planet, and really think about the fact that about 70% of the planet is covered by the ocean, the majority of the planet can't be seen. So it's really hidden from us by the water. But we have maps like this that show what the shape of the seafloor looks like. So you may think, what do you mean we don't have maps of the seafloor? We're looking at it right here. Well, if we were to peel away the parts of the seafloor that don't actually have measured data, it would look like this. So all these black areas are where we don't have data, and the blues and greens and the shades in between are the places where we do have data. So you can see there are vast areas throughout the global ocean where there's just no data at all. And in fact, only 26% of the ocean has been mapped, and that's based on international compilations of data. What that means is less than half of our planet is still unmapped. So less than half of our planet is mapped. So we still have a long ways to go to actually have a base map of the planet, just the shape of it. So that map that I showed you, all those black areas, those are filled in with what's called predicted bathymetry. And there's a satellite technique that we can use to look at the surface of the water and measure little perturbations in the surface. And we can use an equation, a model, to infer the shape of the seafloor, because the seafloor actually shapes the surface of the water in very little bits. The advantage of this is we have a complete map, as you saw, but the disadvantage is that we have very limited spatial resolution, and the vertical accuracy can be extremely incorrect. I have some examples that I like to show of about 1.5 kilometers of vertical imprecision with this kind of technique. And if we think about the maps that we look at in our phones every day, this is from Google Earth. This is a 1-meter resolution image. You can zoom in and see cars. If you have a driveway in a car, you can zoom in and see the details of your yard and your car. For the ocean, if we were to look at it with the resolution of this satellite technique, the UN would look like this. So very, very little detail. Here at Lamont, we have a very long history of working with ocean mapping data, and a lot of this is based on the operation of our research vessels. From our founding back 75 years ago, we had initially a ship called the Vima, and then we progressed over time to other ships, and our current ship is the Marcus Langseth. From the very founding of Lamont, the premise was to collect as much data as possible, as often as possible. And that, I will show you in the next few slides, is the foundation of a lot of really important discoveries about the seafloor and about the planet. So in the early days of mapping, we used what seems pretty primitive now in terms of techniques, and I'll tell you a little bit more about how that works, but a lot of things were done by hand and with paper. And now, we do things digitally. We have a lot more data, we can visualize it in 3 dimensions, and we can build digital maps. So just to give you a sense of the global extent and impact of Lamont vessels over the years, I just put this little time series together to show you the global extent of the ship tracks over time since we've operated these vessels. So the Lamont ships have been everywhere, all over the world, always collecting a baseline of bathymetry data, which is seafloor depth. I'll tell you more about that in a minute. And the more modern ships have more advanced technology for collecting this kind of data. So in the very early days with the Vima, which was a sailing vessel, again with this premise of collecting as much data as possible, these are some of the tracks in the North Atlantic Ocean. I also want to point out that the founder, or our founding director, Maurice Ewing, there in the picture on the left, is surrounded by men on the ship, because in the early days, women weren't allowed to go to sea. So the men would go out, collect the data, it would come back, and things would happen with it. In terms of mapping with sound, there were precision depth recorders, and basically used, like shown in this top diagram, a sound signal goes out, it travels to the seafloor, it comes back, we measure the time it takes, we know the speed of sound in water, so we can compute distance. And so that allowed us to get records of profiles under the ship as the ship moved along. Some of the very early maps that really had huge impact from Lamont were done by Marie Tharp and Bruce Hazen. You can see some pictures of them working together over the years. Again, she was not allowed to go to sea in her early time here at Lamont because women weren't allowed to go out, but she had an amazing skill for bringing this data together and understanding what it meant. And so if we look at a couple of profiles of data, these are ship tracks, A and B. If you just were to look at it in profile view, it would look like those images over there on the bottom, on the left. But what she did is she tried to stylize these and interpret or put her understanding of what the shape of the seafloor really meant. And then she interpolated effectively between it and filled it in. This was a bit different from the approach that was used at the time. But she used this to create this first map of the Atlantic Ocean, this physiographic diagram, which really changed the way that we look at the seafloor. It has vertical exaggeration, it has 3-dimensionality. You can see shapes in a much different way than you would with a traditional contour map that was the old style of doing it. This is with the international standard when she was doing her work. You really can't see the shape of the seafloor in the same way with this kind of a map. So in addition to changing the way that this data was presented, her work also is considered the spark that ignited the plate tectonics revolution. Part of what she did is she aligned earthquake locations along what came to be known as the Mid-Atlantic Ridge, and this was a huge piece of plate tectonics theory. And so in the beginning, when this was starting to come out, her work was literally dismissed as girl talk, and later it was recognized as a really important observation that helped us really understand a fundamental Earth process. This very famous map from 1977 was the world map by Hazen and Tharp. So her work continued, their work continued for many years, and this was published, made available to the public, so not just scientists, but the general public could get a real sense of the mid-ocean ridges, how they exist in the various ocean basins, and start to see the patterns of how all these pieces fit together. So as technology progressed, we moved from single beam, which is depicted there, to something called multi-beam. So think of it as a fan of sound beams that effectively creates a profile perpendicular to the motion of the ship. So we have, instead of just a profile under the ship as it moves, we have many profiles going together. And what this does is it extends our observational footprint and gives us a lot more information. As this technology moved from military operation or use into the academic space, a lot of work was done here at Lamont capitalizing on this new observational technology. So different software packages were initiated here, some by graduate students at the time. These tools are still used by the community broadly decades later. What's called the Ridge multibeam synthesis started here on this campus to bring together data from a bunch of different providers, different scientists collecting the data to build maps that started to look like this. We started to really move into this digital space, moving from paper to pixel. The Ridge multibeam synthesis led to what's now called the Global Multi-Resolution Topography, which still operates now with funding from the US National Science Foundation. We now bring in data from not just Lamont ships, but all the ships in the US academic research fleet and international data, wherever we can. And you can see we're starting to fill in the map more and more with more data. The data in this synthesis goes back to the 1970s. And we have a variety of tools where you can, people, scientists and the public can access and work with this data. And there's more about this in our tent. You can come visit us and see that. I also wanted to point out that this synthesis has been included in Google Earth for quite a while. So when you zoom in, you'll see down here at the bottom a little attribution to us for having contributed this data. So we're really trying to get the data out into the hands of the public so people understand what's under the water. This just shows you the extent of the Lamont research vessel multi-beam data globally. So these yellow track lines represent over 6 million square kilometers of data just collected by our ships that have moved into these public syntheses. And I wanted to also compare the work of Marie Tharp, so bathymetry synthesis then here at Lamont, with now. So this is from GMRT, our synthesis now, and I'll go back and forth again. It's truly remarkable that with such limited data, Marie Tharp was able to build a map that looks so consistent with what we're able to do today with a lot more data. And just to point out how we're still missing quite a bit, this is the actual coverage. There's still big gaps in here, but we're starting to fill in the puzzle more and more. So what we're really trying to focus on now in our group here at Lamont is capacity transformation. How can we get these tools and techniques that we've refined over the decades into the hands of more people so that we can work on this collaboratively in a distributed way? And some ways that we're trying to do this are obviously promoting data sharing, but also sharing workflows and really just listening to people and trying to understand what they need, where we can find efficiencies, and how we can bring more people into this. A big thing that we always focus on is attribution, recognizing, as Robin was saying, we hold our data very dear, and getting people to come around to data sharing really requires that we acknowledge the work and the effort that goes into it. I think this is where I'm going to pass it on to Tinah. So I'm going to put this here, and I'm going to go have a seat.
Oh, all right, thank you, Vicki. From the introduction that we have, I cannot say more than the work that is being done at Lamont is tremendous and fundamental for advancing ocean floor mapping worldwide. So I'm gonna talk about how the contributions from Lamont fits into international synthesis like CHEPCO. So fact is, for 10 years now, GMRT has been a significant contributor to the international CHEPCO map. You might be asking yourself, what is CHEPCO? Question, have you heard about CHEPCO before? Can you raise your hand? Okay, 1 out of hundreds. So CHEPCO is the general bathymetric chart of the ocean. It aims at providing data, bathymetric data, publicly available, so any one of you interested in downloading some data, you can just go to the website, click your interest area, and then get some data. So it all started back in 1903. It was led by Prince Albert I of Monaco. The picture here is gonna show you it was all gentlemen. You know, women can't go at sea, can't be involved, but it has changed a lot. So over than a century, the community grows, and now it operates under the International Hydrographic Office and Intergovernmental Oceanographic Commission, or UNESCO. It's very important to point that because providing that map is not a single-handed work. It needs collaboration and coordination from different government bodies and institutions. So that's why it's important to have those two international bodies leading the program. And of course, there are guiding committees that helps on the technical side and on the social side of CHEPCO. And for that map to be done, there's the Seabed 2030 project that is an accelerator for that map. It's an international effort. The goal is to have 100% of the world ocean mapped by 2030. It is funded by the Nippon Foundation, and it all started around 2017. But I wanted to point that it has an approach where we have several centers around the world, and very luckily, Lamont hosts one of the centers. The center is in charge of the Atlantic and Indian Oceans that covers around 40% of the global ocean. It's huge. But we have a team that's really working on it, and you will see what we do. But apart from that, the role of that center is first to understand what the community needs. We try as much as we can to share our knowledge, make sure that we are all on the same page when it comes to techniques and how to use data. And something that is very important, most of the time when we talk about data, people are very, not gonna say selfish, but they're really holding dear to it. So it's sometimes hard to get it. We try as much as we can to shift that culture and make a change in that, you know, data is not, it's worthy when you share it so people can use it, reuse it into changes for technology and, you know, for science. So what Seabed 2030 has been doing since the inception. So in 2014, that was the time when the first map, I would say the official JEPCO map was rendered. And as you can see, we have more gaps than mapped areas. And this is 6%. Those data that were contributed were mostly sparse data and interpolated grids. And this is what people at the time could find. Now, it's been over 20 years now. And look, we've been, so far we have 26% mapped. There's still much more to do. We know that data is out there, and we are setting all the gears and all the mechanism to have access to that, and also to have people contribute. So as I said, since 2019, we had the first JEPCO map under Seabed 2030, and you can see there is a steady progress. But within that steady progress, there are challenges that we are able to tackle because of the community. And of course, we can't do that on our own. We need people to help us. So it's like a reciprocal relationship around bathymetry data. So I can say that at global and regional, and at local and regional scale, there is a transformation in the way of thinking about data, especially bathymetry data. So you can see here on the pictures, people from around the world that comes to the consciousness that, oh man, we need to do something about first understanding more about the ocean floor, because it links to, you know, blue economy, ocean science, policy making. So yeah, there is a huge community behind the works that is done, and Lamont is probably the core to push that moving forward. So let's talk a little bit about what these people are doing. So first, I'm going to talk about a network of professionals in ocean mapping, and that is funded by the Nippon Foundation. Actually, I am an alum from the Nippon Foundation JEPCO training. It's a 12-month program where you learn all about seafloor mapping, the techniques, but also how to network and take advantage of the big network that exists out there to make changes where you come from first and around you. So today, it's running the 20th batch of scholars. It's based at the University of New Hampshire. And each of these scholars are paying back to the community in some ways by either contributing in initiatives, mapping initiatives, or exchanging skills. So myself, I was part of this project. It's still going. So it's called the Western Indian Ocean Bathymetry. The goal is to create the first map of the ocean for that region. It's led by 5 alumni from the training. And we just had, I think, the second workshop for data sharing and data compilation in Madagascar last month. Part of our goal is to enrich CHEBCO. So it's like, I like to think of it as a piece of the puzzle that's gonna, expand around Africa and the Indian Ocean. And what do people gain from being part of this project and other similar projects like this? So by collaborating with Seabed 2030, if they have mapping initiative, they gain understanding of how bathymetry data is, how it is worked around and compiled, not just for the project Seabed 2030, but at local scale. And then on our side, we would identify and listen to them, what are their needs. And especially for this project, we are looking into the challenges and help them address those challenges. And we use an inclusive approach, so any stakeholders, any enthusiast of the ocean science can contribute. And on to that, I'm just gonna pass to Sheila to hear more about initiatives in ocean floor realm.
Hello. So now, now something that has been happening in recent years is that there has been an emergence in the type of technology that is able to collect this type of seafloor mapping data that we've been talking about. And this picture basically shows all of those different types of data. We can have, for example, like now we can have drones, we can have remotely operated vehicles. They can be above water or they can also be underwater. And all of these different methods have just emerged, and they have been able to provide us with more data through different means that it's not only through, let's say, for example, multi-beam or single beam that we have been talking about in this presentation. And among those methods also there's satellite. And you may remember from one of Vicki's slides that she mentioned how predicted bathymetry from satellites has limited resolution. And this is still true. However, that applies, we would say, for the deep water, which is obviously majority of the ocean. If we try to use satellites to get seafloor mapping data for the coastal waters or shallow waters, we actually get really good resolution. It goes as deep as 30 meters. So that can be very useful for those areas, let's say, for example, in the Caribbean countries that have obviously a lot of shallow water. And yeah, so on that note, it's a privilege that I was able to be part of this, this project. We were able to do this training in the Dominican Republic to do capacity building and training on how to work and obtain satellite-derived bathymetry, which is the name for this type of data. So this data was generated basically by the Dominican Navy for Dominicans. Now the country, when this training was concluded, now the country is able to have, they can visualize what the underwater seafloor data looks like in their coastal areas, which is really important because this is the first time that they would be able to do it with this type of technology. And yeah, it's just, we collaborated with industry partners to do this, and it was just a really, really good contribution. And also contribution because it was also added to the Seabed 2030 project, the data resulted from this initiative. Now, as you have seen in the presentation as well, something that we focus a lot in our team is about the community. what does the community need. And when we were planning this training, we asked them, is there anything else that you might need that we might be able to help with? And they mentioned sargassum. In the case that you don't know what sargassum is, this is a type of seaweed that grows in the warm waters of the Atlantic Ocean. And that's fine, but obviously we put global warming into the context. Global warming has made it that obviously the waters are warmer, therefore it makes this seaweed to grow at exponential rates. And that makes it so that when it goes to like shore and on the beach at very high quantities. And this affects tourism very strongly, especially if you consider Caribbean countries that they depend a lot on tourism in order to thrive in the economy. This is really bad. Personally, like if you get close to this in the beach, like it smells terrible. You don't want to be close to it. They have to close everything. So yeah, it really affects it. So thankfully we were able to provide this additional type of training because the same type of technology that is used to obtain satellite-derived bathymetry can also be used to detect sargassum. So by training them in this, they're able to detect the sargassum before it even goes to shore. So that was really cool. And something else that we do in our team is the Seafloor Data Apprenticeship. We get students, undergraduate students at different levels of college, and we also get participants from the JEPCO training program that Tinah mentioned. And through this summer apprenticeship, the participants are able to get hands-on experience with data management, make sure that the data is of quality before it goes into our data assembly. They can also participate in a stakeholder engagement, both local and globally. And yeah, it's just a really cool initiative that we have. I actually started as this 2 years ago, and now I'm still here. They're stuck with me, sadly. And another really cool initiative that we have is the Girl Talk program. We want to take empowerment in the Girl Talk phrase that was used initially to diminish the work that Marie Tharp was doing. So yeah, we have this program, and basically we have the phrase of Women Inspiring Women in STEM, which stands for Science, Technology, Engineering, Arts, and Math. And we really just want to make women or gender non-conforming individuals to get interested in careers in ocean science, to learn about ocean floor mapping, which is probably what Marie Tharp would have wanted, and just give the opportunity to more people to be interested in this subject. We had our first cohort this past January. Hopefully we'll be able to do it again. And it was really cool. We had basically students, again, from different college levels. And we also had early career professionals that will be interested in this field. And yeah, so the main message, I guess, is that as we can see, we are in a new era of ocean mapping. Compared to let's say 60, 70 years ago, we have progressed a lot. There's a lot of new technologies that we can use to get seafloor mapping data. We have, the culture is changing slowly. People are willing to share more data, knowledge, tools as the things that we're doing. We're not the only people that are doing this work. There's other people that are also focusing on community, on equity. It's a growing momentum and culture shift that is happening. There's a diverse global coalition of people involved in this, and obviously there's way more opportunities to engage. And these are all cute pictures of things Tinah is here, Vicki's here, and I'm here in the back. And obviously, this is a really good picture that we have. I like it a lot because obviously, initially it was like this, right? A bunch of men. And now we have progressed, and now it's shifting. Now it's more inclusive. We have more people involved in this, and it's really cool. So yeah. Okay.
So I get to run the questions. And there's a mic, so everybody can hear. There's one on either side. Are there any questions for Vicki, Tinah, or Sheila? Here's one right there. There's one in the front and then one in the back. And the mic's coming to you.
With all of this data, it would be easy to create an AI algorithm to identify mineral deposit locations and search for other mineral locations with similar structure, as well as areas where noxious vegetable material is formed, and isolate those and find out where it's likely to occur again. Has anybody looked into doing that?
Yeah, that's a great question. So the reality is that most of the data that we're working with is relatively low resolution. We're talking 100-meter resolution at best, and that's mostly in the shallow water. So, you know, the size of a football field is 1 pixel in these maps. A lot of the kinds of scenarios that you described would require higher resolution. There is a lot of effort being put into kind of getting ready for the future of AI and these kinds of algorithms that can leverage this kind of data, but we're not really there yet on a global scale. In small focused areas where we have a lot of data density that's high resolution, we can start to do things like automate various things, whether it's processing or creating the products or extracting information. But at a global scale, we're still not quite there. One of the things that we are very strongly advocating for in the context of, in particular, Seabed 2030, is to make sure that we're not just building a grid, because in 10, 15 years, that grid will be outdated for many reasons. We want to really push on this concept of data sharing so that we're future-proofing for these algorithms that will become more and more applicable to this kind of work.
Okay, there's a question in the back, and then the one on the aisle. All the way in the back? Right under the clock.
Yeah,
No, under.
Basically, my question was around the AI as well, to see how is AI being applied to the work you're doing now.
So I'll repeat it just for the recording that it's again about AI. And I think that right now the best way that AI is being applied is in trying to accelerate the human effort in processing. And again, the work that we're doing, it's kind of like fruit salad, like very different kinds of data. And so there's still a lot of human in the loop kind of work, but trying to figure out where human effort is most optimized and where we can leverage tools is part of the evolution that we're in the midst of, right?
So I have 2 questions. Is that okay? So the first one is, how would mapping the seafloor help in efforts of conservation? I'm very interested in that. Like, what would that entail?
Tinah, do you want to do that one?
Yeah, I can take that one. So I like to think that we cannot conserve or do any conservation action without knowing what's underneath the ocean. So I would think of, part of conservation is understanding the ecology of the species that you try to protect. And habitat mapping can be improved and advance all your initiatives with some bathymetric map. Of course, it could be at high resolution, but it's necessary to first make the decision on the science that you do, and then help the policymaker understand better what's the context of your action. So yeah, that's the relationship between conservation and mapping the ocean floor.
Okay, thank you so
And
much.
I'll just jump in with an aside, in that the project that Vicki and I did mapping the Hudson River, that was actually funded by New York State Department of Environmental Conservation, because they wanted to be able to develop good habitat maps of the base of the Hudson. And they didn't think those boring, as I call them, the boring blue and white contoured maps were helping them.
Oh, that's really interesting. Thank you so much. My second question is more like in the realm of like the professional world. I'm starting to do like research. I'm pursuing my associates at RCC in environmental science, and I'm doing. I'm now in my 2nd semester of research, a different research project. It's related to lichen growths and like stress responses after exposure to pollutants. So it's more in the plant science world. But I find this to be incredibly interesting. And I do want to explore more research in other areas as well. How would you recommend that I start breaking into just research in general? Like, I feel like I'm starting to take baby steps, but I don't think I've fully like explored it yet and like dipped my feet in yet.
So the first way that I will jump in on that is to say that there are many different programs offered here and at other places that can help bring you in. Mm-hmm. Maybe Sheila, you want to jump in on this?
Hello. So I identify with you because I actually graduated from the same major just 2 years ago. And actually, the way that I got here is because someone recommended to me that I just should talk to the professors that I had, obviously that I had a good relationship with and that I had a good class, like I did well in the class, and just ask them if they knew about anything. I emphasize a lot in the power of networking, and the first space that you have to network is literally your professors at school. So when I talked to one of them, she was like, oh, I have a friend Vicki who's hiring this summer, and that's literally how I got here. So you never know who, when you ask like where that's gonna take you, so I feel like the first step would be to talk to those professors in classes that you liked, and just go from there.
Thank you so much.
Hi, I have a question. As far as I know, there are negotiations going on in Jamaica about commercial exploitation of all the minerals that are hidden on our seabeds. And the problem is, the challenge is that most of the seabed is not owned by any state. So you need a regulation, and this is really, really important because we need the minerals for our electric cars and for our computers and so on. And so you didn't mention that. Could you say a little bit about the relation between your work and these really, really important negotiations and hard negotiations going on?
Yeah, so this is a very hot topic for various reasons. And again, I think part of the response is that the resolution that we're working at is coarser than much of what would be needed, and even the data types to do this kind of mineral exploration work. Another way that I would answer is that, as Tinah was saying, we don't really know what's there, so having a map is the first step. It's not our role to be the policy setters, but policy is informed by good data. So in some ways, we're helping and to balance that out. There's also a lot of data that's been collected in the mineral exploration realm that we know exists that is not in the maps that we're building. And so we're kind of operating in parallel spheres with some overlap. It'll be very interesting to see how things evolve. Certainly, one of the main principles and mission points of Seabed 2030 is really to inform good policy decisions and to promote sustainable use of ocean resources. So that's our objective. There's other spaces where there is some liability in revealing what's on the seafloor, but the general feeling and thought is that having this base information is really important and valuable, and this project, Seabed 2030, is actually one of the programs of the UN Decade of Ocean Science for Sustainable Development. So it's recognized in that realm that this is a really critical base of information that we really need to build as a global community.
One more, I think that, and then there, and I think.
Could I just add something in response to your question? I worked for the UN for many years in the area of water resources. So, of course, the basis of the international agreement was the law of the sea. And, of course, the U.S. didn't sign it. We had been, Carter's administration, this was back in the 70s, had been negotiating this law of the sea for 7 years, and almost all the other countries agreed to all of our demands, all the U.S. demands. And then when Reagan came in, like the second day he came in, he rejected it. It was like Trump rejecting the Paris Agreement. Everybody had agreed. So, of course, the U.S. still has not ratified the law of the sea, but most of the other countries are in agreement on certain basic principles of how to share the data and whether or not you have access to the mineral resources. But it's an important agreement, even though the U.S. hasn't signed it.
Great, and there's, I guess we'll do that, and then here, and we'll call it.
Quick question. Thank you. Is including the commercial vessels or cargo ships into the mapping effort, does it make sense? Is it possible?
Yes. Do you want me to take it or do you want to take it?
I can start and then you can. Yeah, so Probably it was like overlooked in the presentation, but the data that comes into seabed 2030 comes from both several backgrounds, including industry, academia, and vessels of opportunity, which is a big thing right now. So yes, we want all hands on board, if I may say, and commercial data constitute a huge, I would say, a huge pool of, contribution in our compilation. So the answer probably is yes, that we have, it's important to point to those type of data.
I can also add that in the context of the Ocean Decade, there's actually a working group focused on figuring out how to get commercial data into the scientific space, because there's a lot of data that's out there, not just bathymetry, but lots of different data types that we don't yet have access to. And so hopefully through the UN Decade, that's going to help release some of that data.
My question is, you just mentioned that you received some funding recently from the New York Department of Environmental Conservation. So I'm wondering, like, where else do you usually get your funding from?
That was old.
That was old. That's. Oh.
So for seabed 2030, the project itself is primarily funded by a philanthropic organization in Japan called the Nippon Foundation. And they've partnered with JEBCO to really accelerate progress toward these goals that seabed 2030 has put out. Ocean mapping writ large at a variety of scales can get funding from a huge variety of sources. There's towns need to do surveys for local things, states need to do surveys, the federal government does surveys, the research community collects data. So there's all these different ways that this work gets funded. There's even philanthropies that are focused on ocean exploration that are collecting some of this data and funding scientists with ship time to go to sea to collect data and answer big science questions.
Thank you. All right, I think we have to call it quits. I'm sorry to the last questions. I'm getting from the back.
But come to our tent and talk to us.
Right, come to our tent. These guys will be around all day. And why don't we give them one more round of applause, please.
slide advancer, forward, back, laser pointer.
Okay, perfect. Yeah, just make sure it works. Okay, thank you.
No problem.
Test, test. Test, test. Oh, okay. All right, so I think we can go ahead and get started. Thanks everybody for coming. I know it's a really nice day outside, so thanks for being in this room for me for the next 30 minutes or so. So my name is Dan Westervelt. I'm a professor here at the Lamont-Doherty Earth Observatory, this campus that you're at. I work on climate change, air pollution, and so I'm going to talk a little bit about those things that I work on today. These are just some photos here. I think everybody that lives in this area and was here last summer probably remembers this picture in the bottom center here. We had, that crazy wildfire event from Canada, and so this was this is supposed to be the a view of Manhattan, but you can't really see anything. I guess if you look really close, you can sort of see some outlines of buildings, but it's mostly pretty obscured. And this was just a few, this is Jake Tapper and me talking about it on CNN, and then another instance right there. So at the end, if you have any questions about the wildfire event and all that, I'm happy to talk about it. So I want to start off with this slide here. And the take-home message of this is that high-quality air pollution data is very sparse around the world. So there's just not a lot of it. And what this graph is, or what this map is showing, is the number of air quality monitors per million people. Okay, so it's like the density of the air quality monitors in each country. And so if it's green, there's greater than 5 per mil. Yellow, 1 to 5, and red is less than 1. And then if it's no colors at all, like gray here, that means that there's no known air quality monitoring. So before you can even think about controlling the air pollution and mitigating the air pollution, you need to know what you're dealing with. You need to be able to monitor it. So there's an old saying that says you can't manage what you don't measure. And so in many places, especially in the low and middle income countries, so we're talking about many countries in South America, many countries in sub-Saharan Africa, many countries in Asia, we have a real limited ability to understand our air pollution and therefore know how to mitigate it. Some of the more wealthy countries, in the US, we have a fairly good coverage. But even there's still some lacking of data, and we can talk more about that later. So the map that I was showing there is specifically referring to monitors that measure fine particulate matter, or PM 2.5. Okay, so PM 2.5 is, as you'll see in a second, the main culprit when it comes to impacting people's health. And that's one of the main reasons we care about air pollution, is that it impacts your health. You can get sick from it, you can get asthma, you can die prematurely. And so it's a real public health crisis. What is PM 2.5? Well, this is a kind of a schematic of what it is, but it basically refers to particles in the atmosphere that are smaller than 2.5 micrometers in their length or in their diameter. Okay, so if you look at this picture here, we have some kind of scale representations that you can look at, versus a human hair or a grain of beach sand. These particles are much, much smaller than that, and for the most part invisible. We don't really see this. So air pollution is sometimes thought of as an invisible killer because we don't often see the pollution that well. And so exposure to air pollution is actually the second leading risk factor for premature death around the world. So if you look here on the left, these are the activities that you can take, that you can do, that are most likely to give you a higher chance of premature mortality. And so the number one is high blood pressure. I think that makes sense to a lot of people. But somewhat surprisingly, just air pollution, just breathing, is the second most riskiest thing you can do for dying prematurely. And it's ahead of things that we often think of as more not ideal behaviors, things like smoking tobacco, poor diet, high fasting plasma glucose, So it really is truly a big issue. And the statistics are showing that approximately 8 million people every year die prematurely due to exposure to different air pollutants. So we got these two maps here. You're probably wondering what's going on here. This is basically showing the number of deaths per million people due to PM 2.5 split up by country. Okay, so these darker colors are showing higher numbers of deaths per 100,000, not per million. The top plot is showing just the ambient PM 2.5, which means just the stuff that's kind of out in the environment, comes from our tailpipes of our cars, comes from different burning of waste and of vegetation, comes from power plants, all that stuff. The bottom plot is called what we call household PM 2.5. And this is chemically very similar to the ambient and physically very similar to the ambient PM 2.5, but this is stuff that's more indoors. And so you see a lot of premature deaths attributed to household PM 2.5 in lower and middle income countries. And part of the reason for that is because the practice of cooking in many of these countries is done using things like wood or charcoal because it's cheap, it's free. And sometimes wood is just free. You can just go out into your wilderness and chop down a tree and use that to cook your food. So you get a high amount of exposure to to that situation in some of the lower income countries. And oftentimes the cooking happens indoors as well. So these are not always kind of outdoors. And maybe if you're lucky, maybe there's a chimney or an open window, but a lot of times that's not the case either. So summary is that we have a really high health burden due to exposure to PM 2.5 in a couple of different ways. And without getting into the details on this plot here, this graph, this is just kind of to make the point that air pollution, especially fine particles, impact almost every system and every organ of our bodies. So the obvious kind of method of introducing the particles to our bodies is through the lungs. Not surprisingly, we breathe it in. But the particles are often small enough that they can cross over kind of this lung-blood barrier, basically. They can get into the bloodstream. And so they cause all kinds of different cardiovascular ailments as well. And actually, that's the number one, if you break down the deaths by cause, it's actually the cardiovascular, the heart-related things that have the most mortality. But it affects everything, including the brain. I don't even have reproductive systems up here, but it affects that as well. So almost every organ and every part of our bodies are impacted negatively by air pollution. So this is just a little graph here. So a lot of our, as you saw earlier, the air pollution problems are often exacerbated in lower income countries. And so this is some data we took in Nairobi, Kenya, which is in East Africa. This is a map. That's Nairobi, Indian Ocean. So it's in East Africa. And we had here on this location 2 filters. One is just a blank filter. So this is just some Teflon, basically. And on the left is a filter that had been collecting particles for a couple of weeks. All right, and so you can see this, very pitch black collection of particles, basically, that are caked on there over 2 weeks. And this was in a very busy area. It's a highly trafficked, lots of vehicles, buses, trucks, cars. So it's not too surprising, but you can imagine, all of this depositing instead of on these filters. If you're living there for 2 weeks, then it's depositing on your lungs, and you can imagine that's going to have a pretty negative health impact. So what are we doing here at Lamont about this? One of the main things we're doing is closing the data gaps in data sparse areas. Okay, so as I mentioned at the very beginning, you can't mitigate what you don't measure. And so in some cases, when there's just absolutely no data, first we need to get some data so that a case can be made to help address the problem, okay? And so we do that. I mentioned some locations in Africa where we've done that work, but also in underserved and overburdened areas of the United States. Okay, so we do have a decently good coverage of data here, but there are certain areas, certain neighborhoods, certain places where that's not true. And those oftentimes are also some of the more polluted areas. So it's really important to note that as well. We're working a lot on training and capacity building, so teaching people about air pollution, really kind of training scientists, especially from international locations, to kind of show them kind of the things that we've learned the hard way, I guess you could say, here, in terms of mitigating the pollution problem. So training. And then the last one is, we are a research institute, so cutting edge air quality research using, novel methodologies to provide actionable information to not just scientists, not just the scientific community, but also policymakers, decision makers, and other stakeholders that, that have the power to address this issue. So I do want to mention some of the places in Africa where we're working, because the air quality problem is especially bad there, and it gets probably the least attention out of all the parts of the world where there's air quality issues. So we're working in, I don't know, like 10 or 12 different cities where we've applied some of these methods. So to give you an example of the monitoring in Africa, this is actually now switching over to West Africa. This is in Accra, Ghana. All right, so this is the Gulf of Guinea. Accra, Ghana is a city of, I think, a few million people. It's rapidly growing. It's right on the coast here. And with a partnership with the Environmental Protection Agency of Ghana and the Ministry of Health of Ghana, we started in 2018 an air quality monitoring project where we put out about 20 different air quality monitors throughout the city. And to our knowledge, it was one of the first, if not the first, efforts at monitoring air quality in this major city. So these dots here are the different locations. There's some of them aren't on this map because we kind of put a lot of them in a very kind of dense informal settlement where air pollution levels were extremely bad. So they didn't show up on this map because they're kind of way too zoomed in for that. But you'll notice these kind of red dots, and in some cases you'll see there's a little bit of like yellow slivers in here. So what's going on there? These are pie charts, all right? And so these pie charts and these percentages are showing the number of days of the year that exceed the World Health Organization healthy guidelines for PM 2.5. All right, and so they're all pretty much red. The numbers are all close to like 99% because almost every day of the year in this city has, unfortunately, unhealthy air quality. And so this is a little bit maybe too detailed, but some of the plots here, these are some of our measurement sites, and so there is some variability. This dashed line here, just for your reference, that's the standard, the World Health Organization healthy guideline. So in theory, all these daily averages, which make up these violins here, all of them should be below this dotted line. But you can see that pretty much all of them are above it. And this is just some of the photos from some of our efforts where we've been working with a lot of local expertise and local scientists to carry out these projects. We're also doing this, as I mentioned, kind of in the United States, and using some really cool data science techniques to extract useful information from sensors, from air quality monitors. This is in Queens. This data comes from Queens. This is the New York State Department of Environmental Conservation kind of flagship monitoring site for New York City. It's on the campus of Queens College. It's one of the reporting stations that New York State and New York City uses to determine whether or not they are within compliance of air quality standards or not. So it's an important place. And so what we wanted to do is they have all this fancy instrumentation. They have millions and millions of dollars of data to enforce and basically to enforce the air quality regulations. And all this, I should mention, all this data is publicly available. This is our data. And by ours, I mean the public. It is funded by our taxes, basically. So this data is all free online. You can get it. But what we wanted to do is, if we could try to see, can we find cheaper alternative to measuring pollution, because to have this fancy station that's in the background of this photo, that's millions of dollars, and that's not going to be possible, especially in resource-limited environments. But so that that includes places in the U.S., but also, of course, across the world. So we wanted to see, can we use a cheaper alternative? And so there's these things called low-cost air sensors. Maybe you've heard of them, but anyone can just kind of go out and buy one. They're a very common brand. There's a brand called Purple Air. If you Google that, you'll see Purple Air. It's about $250, and it's a little air quality monitor that you can put up in your backyard. You plug it in, it connects to Wi-Fi, it gives you the data. There you go. And so a lot of people around the country and the world have taken that on, especially in places impacted by wildfires. So they've went out, some people that are impacted by wildfires, let's say in California, they wanted to see what the levels are. So they go out, they bought a Purple Air, they put it in their backyard or off their apartment railing or something like that, and then that data becomes publicly available. And so this is a really kind of cool idea for democratizing air pollution data, making it more available, closing a lot of these gaps. But one of the big issues is that data any good, all right? Because it's, an order of magnitude cheaper at least. And so you probably get what you pay for in some sense. And so what the scientific kind of role here is that we're trying to use different data science techniques to try to extract useful data out of these kind of lower cost, lower quality data sets. And so what this plot is showing here is what we did is we took some of these lower cost instruments and we co-located them with the New York State regulatory monitors. And so that's what's here. This happened in 2019. This is several years ago, the PM 2.5 concentration. This blue line here is what you get from one of these Purple Air devices, which is one of these low-cost sensors that you can just buy off the shelf. It's about $250. The yellow line is what sort of the New York State regulatory instrumentation is reporting. So you can see there's a pretty big gap there in, the Purple Air, the cheaper one, is sort of overestimating by a fair amount. And so that's kind of a problem because we don't want to sometimes if you give bad data to somebody, that's worse than no data. So we want to be careful with that. And so what we can do is kind of take advantage of these side-by-side data collection and apply some statistical methods. And we do that, and we can bias correct the Purple Air data. And so that's what you get at the red line here. And you can see this red line matches pretty well with kind of the gold standard in this yellow line, all right? So that's a good exercise, but what does that actually do for people? It just shows, okay, these sensors you can make them work well, you can make them be accurate, but that was just, one site. What can we actually, can we do anything with this? Can we achieve impact? And so we've done that a little bit, and this is again in another city in sub-Saharan Africa called Kinshasa in the Democratic Republic of Congo. And so we wrote a paper recently where we used these low-cost devices to investigate the sources of particulate matter. All right, so this is more actionable information. It's one thing just to say, here's the concentrations of particulate matter. They're, X, Y, Z levels. What you really need to know is what is causing it? Where is that X, Y, Z level of pollution coming from? And so that's what we did in this work. And I won't really go too much into the details, but it was fairly successful in that it was able to be used in city action plans, all right? So here we have a screenshot from, this is a Columbia Climate School report with in collaboration with some ministries in Africa, and they basically made a plan for action for air quality and pollution based on our data and based on our recommendations about what the main sources of pollution were. So this is really important to actually, mitigate the problem and achieve impact. So we have this air sensors lab. This is on the roof of the oceanography building. We have a bunch of different, each of these little devices here you see are various off-the-shelf, low-cost sensors. And then what we have here in this picture is kind of the regulatory monitor. And so we do this kind of side-by-side analysis to see how they perform, all right? So yeah, these are kind of the different brands here. You could point to them. This is again, the kind of the fancy one. And then some of these are also kind of just homemade in our lab, all right? So we have some of them that are just we make in my group. So one thing that's really cool about all this is you can come see this today, right now. If you come over to the oceanography tent, which I think is tent 10 or 9, I'm not sure, but it's on the map. You can see some of our sensors. Here's an action shot in the lab where one of our lab members is putting together some of these devices. You can see there's all kinds of wires and microelectronics and things like that. And you can actually go touch one of these and play around with it if you want. So the total for all the parts of this, these cheaper instruments here is something like $50. And you can compare that to the kind of research, or regulatory monitor, which is here, that's going to cost somewhere around $20,000. So there's a huge benefit in trying to get these lower fidelity instruments to work well. All right, so for the last 5 or 10 minutes of my talk here, I want to bring this back to climate change, because the talk did have also a element of what does this mean for climate. So we have all this pollution. The leading driver of climate change, of course, is anthropogenic CO2 emissions. That's undoubtable. However, there's a lot more to the story than that. Some of these same air pollutants that kill 8 million people prematurely every year also have a climate impact. So this is an important take-home message, I would say, is that the air pollutants, we breathe them in, they cause impacts on our health. They also are impacting our climate. And they do it in complex ways. And they also kind of do it in a way that is opposite of CO2, all right? So this is the kicker. This is what makes this problem really difficult, is that we know that CO2 warms the atmosphere. That's, well established. These particulate matter emissions, this PM that's in the atmosphere, has the opposite effect. That cools the atmosphere. So by doing that, by emitting these cooling particles, we've actually masked some of the warming that would have happened otherwise from CO2, all right? And what that also means is that as we reduce those health impacting particles, which is a really good idea, we want to do that, we're going to unmask some of that additional warming, all right? So it's really kind of important to think about. This has been referred to as the Faustian bargain of reducing air pollution, all right? Because we've been, throughout our history as a globe, as a society, we've been emitting these cooling particles, and they've been buying us some time, so to speak, on the amount of warming from CO2. So I found this article, and there's a lot of popular science articles about this now. This one says, how air pollution delayed a surge in extreme rain. So this is kind of a specific example of these pollutants having masked effects of global warming. Here's an image of, this is eastern China, East Coast. You can see from satellite, this is a satellite image, a day where there was extreme smog, extreme pollution. And you can see just basically the entire, eastern half, or this corner of China is completely blanketed in this smoke. And so you can imagine that as these particles kind of exist in the air, they interact with incoming sunlight, all right? In most cases, they scatter, but in some cases, they actually absorb some of that incoming sunlight. And if that sunlight's not reaching the surface of the Earth for that reason, that's going to have an effect on the temperature. It also has effects on the water cycle, agriculture, food, all that stuff. But we'll kind of think about temperature for now. All right, so less of that sunlight is hitting the surface of the Earth. You're getting less warming, and that's why we say that particles mostly cool the climate. So opposite of CO2. And so this becomes a little bit tricky here, because we need to seek strategies for climate policy that are win-win, both for air quality and climate. And it's not always straightforward to do that, because you can take a energy generating unit, a power plant, and you can limit its aerosol or particle emissions without touching its CO2 at all. That's actually very common, and that's one way that we've cleaned up our air in the United States, is by installing these post-emissions engineering treating of pollution units. And they'll scrub out the particles, but they won't do anything for the CO2. And so that's an example of, kind of a lose-lose, I guess, or actually, sorry, a win-lose, because it would improve public health. You get fewer particles, that's great, but you're also going to unmask some of that additional warming All right, so we need to craft strategies that are wins for climate and wins for public health. And if you don't do that, we did a study, we've done a series of studies actually over the last decade. What happens if you don't do that? What happens if you just try to control particles only? It's not really good news. And so this is what you get here. This is the map of the world, and these colors are showing the amount of warming that you would get by the end of the century if you just control the particles. And the answer is, I mean, it varies. On average, it's probably about 1 degree Celsius. And in the Arctic, it can be up to like 3 or 4 or 5 degrees Celsius. So that would be 1 degree, or at certain locations, 3 or 4 degrees, without any touching of CO2. This is mentioning no CO2, no methane, just if we do the nice thing of cleaning up our air pollution so that not as many people die. Just if we do that, we would get this warming. So it's a real kind of paradox. It's sort of like explaining to someone, you're cleaning up the air, but you're getting more global warming. How does that make any sense? That's kind of the point I'm trying to make here. So yeah, just to kind of summarize, I don't want to go too much into the details, but the good news is there are policies, there are pollutants that we can target that are win-win. And what I mean by that is they have warming influences on climate, so reducing them causes cooling, and they also impact our health negatively. So if we can tackle those ones that impact our health negatively and have a warming impact on the climate, then we have a win-win. So a good example of that is black carbon or soot. And it warms the climate, and it also is a particle that we get into our systems. So no one is really suggesting we should keep polluting intentionally to save ourselves from additional warming. That's not really the answer. Of course, we need to reduce the pollution to reduce the 8.1 million people that die prematurely every year, but we need to do it in a way that's sort of joined up with the climate policy so that we don't trade one problem for another. And to talk about air quality policy here for a minute, this is an example from the United States. And the take-home message here is that improved air quality does not come at the cost of the businesses or the economy. All right, and so what I'm showing here is the percent change since 1980 to 2016. And each of these colors are a different item and how it's changed. So let's start at the bottom here, this pink. Due to the Clean Air Act and due to policies and technologies in the United States, pollution emissions have gone down quite a bit, 67% just from 2016 to from 1980. At the same time, things like the GDP have gone up quite a bit, the vehicle miles traveled, so we're driving more, population's gone up, energy consumption's gone up, CO2 emissions have mostly gone up, although they're kind of like flattening out now. But despite all that, we're still achieving reductions in pollution. And so how is that happening? Well, the short answer is, things like more efficient vehicles. So we're not necessarily driving less. As you can see, we're driving more, but our vehicles are getting more efficient. There's more electric vehicles now. You see them all the time. So we can achieve this basically without having to sacrifice kind of a lot of our ways of life. And what's responsible for all this is the US EPA Clean Air Act, which started in the 1970s and it was updated in 1990s. It is probably one of the most successful pieces of legislation in US history, if you care about costs and benefits, I would say. So these are the costs. This little circle down here, it cost about $65 billion over the last 50 years to implement this Clean Air Act. But the benefits have been estimated of this larger circle at about $2 trillion. All right, and so where do those benefits come from? The biggest thing is reduced healthcare costs. All right, so if we have less pollution, fewer people getting sick, fewer people going to the hospitals for visits, we have less mortality, less cases of bronchitis, fewer cases of heart disease, fewer cases of asthma, fewer emergency room visits, et cetera. It also impacts human productivity. So if you're sick, it's harder to work. It also impacts crops, so pollution can damage crops. That's a big part of, agriculture is a big part of our economy as well. So yeah, in the US we've gone from kind of this picture, this is 2005, this is the pollution levels of sulfur dioxide in 2005. This is 2017. If I had the 2024 data, it would look even better, but there's been a huge change here in the pollution levels over time. This is as measured from satellite. And so this is actually not only just good for health, but there's long climate connections that we don't often realize. And so we did a study where we said, if you reduce those pollutants in the US, what impact does that have on climate? I already told you it does warm the planet, which is generally not good. But it's not all bad news, all right? So if we reduce the SO2 over the US, we do get additional warming. That's what these orange and red colors are showing here on this map. These are temperature in Kelvin or degrees Celsius. But that actually has a really interesting effect on the water cycle in that it increases rainfall over Africa, all right? So in this case, reducing this SO2, there was a disbenefit with the warming, but there was a co-benefit with increasing the precipitation over the tropical rain belt in Africa. And you can see here these red colors here are indicating higher levels of precipitation. And this is a very sensitive area that relies on rain basically for livelihood, economic activity, food, survival, et cetera. This is an area where there's a lot of agriculture. It's called the Sahel. It's a region that it's sort of a transition between the desertous Sahara and the green, tropical Africa. So to summarize, there's a lot of reasons to clean the air, climate, air quality, health, water, energy, food. And my take-home points here, air pollution is the second leading risk factor for mortality worldwide. About 8 million people die prematurely each year globally. Air pollutants are also coupled to the climate system, and they have complex impacts on the climate system. But synergies and trade-offs exist for attaining climate and air quality goals. So I think with that, I will just thank the funding and thank my group, and happy to start taking questions. Thank you. We have mics to go around if, in the back and in the front, if somebody wants to ask any questions. That's okay.
Hello. Hello. Thank you for your presentation. Very exciting. I have a question. Is there any difference in the how affects the human health if you have PM 2.5 emissions from cars or from burning wood, for example? I asking this because my country in Chile, in Santiago, the capital, they can't use wood to warm the houses. It's prohibited. But in the south, it's allowed. And in the south, when you go to the south, you see these huge clouds of smog, but caused by this smoke. So is there any difference?
Yeah. So the short answer is yes, there is a difference. The composition of the particles matters a lot. So I was treating particles as just some one big black box, and that's actually how it's mostly regulated right now. But within that characterization, you have different chemical makeup of particles. You have some particles that are organic compounds, you have some particles that are inorganic. And generally speaking, we think that the organic ones are a little bit more toxic, carcinogenic. So it really does matter what the emission source is. And that's one of the reasons why it's really important to not just characterize the total concentrations, but also kind of understand what are the different sources. And that's also a really kind of new research area. So the reason why that all health policies and regulations are based just on the total concentration is that we just don't have enough research to know, which types of particles are necessarily more lethal than others. And in terms of the cook stoves and the fires and stuff, yeah, I mean, there's a kind of a range of things that can be done. The fires, if you're just kind of open burning, some wood or some charcoal, you get really kind of rough pollution. But there are solutions that kind of transition to healthier levels. There's things like LPG, which is it is a fossil fuel, but it burns a lot cleaner. It saves a lot of lives in terms of the pollution levels, and it also saves a lot of CO2 emissions. So long term, people probably that are using these kind of cooking activities, they probably want to switch long term to like solar or electric or something that is, ultimately clean. But LPG in particular can be a nice transition fuel that allows us to achieve some of these impacts, save some lives without completely getting too idealistic. What is LPG? So it's basically just pressurized natural gas. Yeah, and if you've ever gone camping and you have you buy these little cook stoves with those green Coleman tanks, that's essentially what that is. Yeah. It does, yeah, it does, but at a much lower level than just lighting some coal or lighting some wood. Yeah.
So you talked about the impacts of pollution on climate change. I was wondering if you could say a few words about the impact of climate change on pollution. Like you alluded to the wildfires, that's one example, but are there other examples where climate change might actually make pollution better or worse?
Yeah, that is a really good point. It's definitely a two-way street. It's not just air pollution impacting climate, it goes the other way as well. So the wildfires, we think that fires are getting larger due to climate change, and that of course has impacts on air quality, but impacts beyond air quality as well. Warmer temperatures, if you just don't even think about the fires, warmer temperatures have a lot of different feedbacks on air quality beyond that. One is the hotter it gets, the more people are going to be running air conditioners, demanding electricity, they're gonna need a lot. And so you get higher emissions during heat waves for that exact reason. When we have these crazy heat waves in New York City, their emission levels are higher because people are running their ACs at the lowest levels 24/7. There's also all kinds of different impacts on the water cycle. So one of the main ways that particles get removed from the atmosphere is by rain. So after a rain event, air quality is great. The water kind of washes everything out. But climate change is going to affect rainfall patterns in a big way. We can have some drought conditions, we can have some flooding conditions, and so there's a feedback there that impacts air pollution as well. Generally speaking, if you had to give it a short answer, you would say that warmer temperatures, future climate change generally is going to make air quality levels slightly worse, so it's a negative.
Hello, I was wondering, often it's said that hurricanes have greater ferocity because of the temperature of the ocean. I was wondering, to what extent do we have data on the temperature of the ocean? For example, do we have a temperature of the Gulf waters and other places? Thank you.
Yeah, so we have sea surface temperatures historically probably back to, I think, the 1880s or so. That's when thermometers became a thing. The way that, or I should say where they became more widespread, the way that we typically generate global sea surface temperatures is a combination of actual thermometers and also remote sensing. So satellites and other equipment that can sort of indirectly calculate temperature from that. So we generally have pretty good sea surface temperature data from the 1880s to present at a fairly high resolution. So you could say, on the order of, I think, tens or hundreds of meters on the ocean surface. So the data is pretty good. I'm not a hurricane expert, so I won't comment further on that. But there are folks here at Lamont that definitely could answer that question further.
So I had a couple questions about monitoring air quality and what your team is doing in general. First of all, for things that for the air quality monitors that could just be commercially bought, what would you recommend? Because I'm a big fan of citizen science. What air quality monitor would you recommend one could purchase that would be the most accurate in terms of data? And how accurate would you say it would be? Is it still highly inaccurate? It's just the least inaccurate, or is it fairly accurate?
Yeah, another really good question. So I'd say the most, you can't go wrong with Purple Air. I would say that's one of the the good ones. There's another company called Air Gradient, which I've had some good data with. When you actually look at so all these different companies that are making these things, they're all using kind of the same measurement principle technology.
Okay.
They all just have a little like laser that basically shines light at the particles, and then what it does is it measures the amount of light that's scattered from those particles. So you know, you kind of have to look under the hood a little bit and realize that in the actual measurement, a lot of the companies are using the exact same technology, and then it's sort of the peripherals that are sometimes different. Like one will offer Wi-Fi connection, one will offer cellular connection,
I see.
solar power, whatever. So in terms of, you know, so those two are good. In terms of accuracy, it's very environment specific, all right? So if I had to give it, you know, kind of a percentage, you know, I'd say within like 25% accuracy. Here's one way that I often think about it. We have these things called, I didn't talk about this, we have these things called like air quality indices, and we have different categories, and they're color coded. Green is good, yellow is moderate, red is unhealthy, purple is like hazardous, so on. The sensors are usually good enough to get that right. So they may not get like, is it on the upper end of the unhealthy, or is it just barely in the unhealthy? But they'll get the overall like color right. So yeah.
Okay. And would we, like, if, for example, I were to buy, like, let's say purple air and, like, collect the data from it, would I be able to submit it to, like, for example, your team, and then, like, you would be able to, from that data, bring it down to more accurate numbers, or would it have to be through that machine that you had at that, like, at your station?
Yeah, so they actually already offer a correction factor. You can, on their map, their website, you can just say, like, click a box, basically, that says
awesome.
correct the data. And it does usually, you know, end up being somewhat environment specific, right? Because the things that affect the way that you sense the particles include like the local emission sources, include the local humidity, relative humidity, local temperature. So that varies. So you wouldn't necessarily want to like apply it globally, but you know, just applying it within, you know, a region or within the U.S., they've developed a sort of correction factor that actually the U.S. EPA has developed a correction factor for purple air that applies to, that in theory applies everywhere to the US. So yeah, you don't even have to do anything. You can just sort of click that option on their website.
Great. Yeah. And then, so how is your team dealing with like keeping track of like air quality, and like what does your team do in general? I'm very interested in that.
Yeah, I mean, we build some of these things ourselves a little bit, you know, just to get a better understanding of them in some sense as like a research activity. We also work a lot on trying different data science approaches like machine learning or regressions to come up with better correction factors that can be as accurate as possible, and that also can be applied to different parts of the world. Because as I mentioned, it's very regional specific. You wouldn't want to develop a correction that you did here in New York and apply it to sub-Saharan Africa or India or something like that. It's just the environmental conditions are so different. So we spend a lot of time on that. We also, you know, it's not just necessarily about like that, it's also about sort of understanding the differences hyper-locally in pollution levels. Like what happens if you know, to give New York as an example, you know, the Upper West Side near Columbia versus Midtown versus the Lower East Side, you know, sort of on that hyper-local level, what are the differences and what are the different sources of pollution? So we spend a lot of time on that too.
Okay, thank you so much for answering my questions.
Yeah, no problem. There's one in the there and then one in the back.
So I am a high school science teacher, and I remember when the sky turned orange last year, and that was an eye-opening event for my students as well. I'm just wondering if you've seen a difference in the public's view of air quality since we've had these major events. And a side note, I've also noticed some places now publicly posting with the flags the air quality for the day. So has the public's view of air quality changed since these major events have been happening?
Yeah. I would say a little bit. There's sort of like diminishing returns. So early on, you know, in like the first few months afterwards, I talked to a lot of people that were like, "Oh, what's the AQI today?" You know, because it was sort of fresh in their mind. You know, we're kind of a bit delayed from that now, a bit far out. But I will say that I'm seeing more. You know, like I think iPhones now give you an option to put the AQI on your home screen, and so I am seeing little things like that suggest that people are getting more and more into it. You know, it may be a little disappointing how quickly it sort of faded, but yeah, it does seem like it has caught some wind. Yeah.
So there's been a shift in the building trades industry from, you know, back in the day we had older furnaces and things like that, and then they actually got their efficiency up. And it was like, oh, natural gas. And now there's a shift in the industry where more people are going to electric heat pumps. Does that research benefit like the EPA, the USGBC, United States Green Building Council? Has that been the reason for this shift, is for the emissions for these things, or just trying to cut down on what they're putting out there?
Most of the time I see that framed as reducing CO2. Even though you're going from, like coal to gas, or you're improving efficiency, I usually, like New York State, for example, has all these very ambitious goals for greenhouse gas cutting and for electric vehicles and things like that. So I usually see it framed that way, but there's definitely co-benefits. If you're trying to reduce CO2, in some cases you can also reduce a lot of your particles. Yeah.
I mean, it was funny, for years and years, it's like, gas stoves and things like that. Now we're going back to electric stoves. Nobody and their brother did electric heat because it was so bloody expensive.
Right. Yeah, I mean, the argument is that the electric grid is a little bit cleaner than, just 100% gas, I think. And that's also kind of one of the reasons for the boom in electric cars is, it's as opposed to just filling up your gas tank, you could have a somewhat lower CO2 emissions and somewhat lower air pollutant emissions as well. But there's definitely a lot of unknowns and definitely a lot of questions. Can the grid handle all that capacity? Can it, is that going to overflood the system and everything going to black out at some day? So.
Which is funny because there was just an article this morning at CNN about how the grid is, that Helene and Milton, the grid is about 60, 70 years old, and then we are piling all this stuff on it, including electric cars, myself included.
Mm-hmm.
Like, okay, at what point are we going to reach a tipping point?
Yeah, it's an open question, I think. Yeah.
Thank you.
Yeah, sure.
I've been walking around and seeing a lot of the abstracts and the work you guys do. A lot of it has profound public impact in terms of the research. Could you talk about how some of this research gets through to the public? Because some of it, frankly, has a big challenge in sort of in that public education aspect. When does it work well? Have you seen experiences in other countries where it works better? And some frustrations maybe you or the faculty have here in terms of some of the research you guys have. How does it get through to the public in a better way?
Yeah, I mean, that's a real challenge. We're mostly trained as physical scientists, so we don't necessarily have all those science to policy credentials. Events like this, I think, are good for just spreading general awareness, but a lot of us do kind of partner with different decision-making agencies, like the Environmental Protection Agency. We work with them. There's a lot of people here that work with different meteorological agencies and climate agencies. So I think just sort of partnering with them and also partnering with policy experts like in the universities, like Columbia has a school of public affairs and things like that. So that's kind of the strategy is to approach it that way and just keep producing the best science we can.
Hi, I'm going to have to cut this off because there's going to be another talk here at 1 o'clock. But before you leave, I'd like to just say thank you for coming here and thank Dan for giving such a great and illuminating talk today. Okay, and my name is Steve Goldstein. I'm the interim director of Lamont-Doherty. And I just want to say before you leave that if these programs that you see here today are of interest to you, I'd like to invite you to attend our public lecture series. Okay, and our next event will be held in the evening on Wednesday, November 13th, so it's just in a few weeks. It will be about hurricanes, and it'll be very interesting, and you can learn more about it and register at the table in the lobby right outside here. So mark your calendars, and please come back. Okay.
Yeah, no, it's a busy day. Yeah, I appreciate it. Thanks for coming by. All right. We'll go mingle.
That was a great talk.
Thank
anyway.
you. Yeah, I'm glad to have done it.
Your first slide is right after this, and after your last slide is a blackout in case you want to go to mid-stage and not have the projector in your
I know, I'm thinking that's fine. Yeah, that's the
I have it muted, so it's live now, and I'll mute it.
Okay, so you can open it.
Yes.
When you
get behind the podium, I'll mute it.
Oh, okay. So can you actually get copy of it?
Art is going to do this slide advancer is forward, back.
Okay. I always have trouble with this forward, back. Okay. So I need to go back to the one. This way, right?
Yeah, please don't put your slide on. I just put it in between just in case.
Yeah, that's fine. And then maybe I just put on this one because that's actually
Well, good afternoon, everyone, and welcome to our 2024 Lamont Open House. It's a pleasure to see you all. I'm Art Lerner-Lamb. I'm a senior scientist here and one of the scientists serving a life sentence here at Lamont. Been here a while. You may have also noticed that this is our 75th anniversary. And I'm not quite that old, but still, this is a remarkable anniversary for our institution in the sense that we are trying to get a grasp of what we've been able to accomplish over the last 75 years, in particular, what it means for how we live on our planet. And we hope that we'll be able to do that for the next 75 years with the support of the public like you and the interests of the public and so on. So a lot is happening here at the observatory. And one of the things that has really come to the fore in recent years is trying to apply the basic research we do in the earth and environment into how we live. What is it that we do to make our world more sustainable? How do we live sustainable lives? How do we live in a healthy atmosphere, healthy oceans, and in this case, how do we live with plastics? It probably comes as a surprise to you. It certainly came as a surprise to me that, there's so much material in our lives, and to find out that one of the most basic materials in our modern life, plastics, happens to be everywhere and doesn't disappear when you throw something out in the trash, it really amazes me. And one of the scientists who has been foremost working on this problem and who has contributed greatly to the not only the scientific literature, but also the public awareness of what's happening with microplastics and now nanoplastics, is my colleague Beizhan. So let's turn it over to Beizhan. He'll speak for a while, and then we'll have an audience question and answer. Thank you.
Thank you, Art. So yeah, my name is Beizhan. I'm a Lamont research professor here at Lamont-Doherty. And what I'm going to talk about today is basically the ecological and health impact of the nano and the microplastics, and also what is our engineered solution for that. Okay, so first let's define the problem. So by 2023, more than 10 billion metric tons of plastic waste will have been produced globally, and has been produced, and then there's about like 6 billion tons of the waste has been discarded into the environments. So you think about it. So we can see that starting from 1950s, the plastic production was dramatically increased, and this is kind of exponentially increased. And then while we are produce them, and then about like 1/3 are still in the usage, like in the car, in your, like buildings. However, we only recycle about 10%. And we left about like a 2/3 was discarded in the environments. And these discarded environments can cause trouble is that, they are basically causing the trouble that they can entangle the animals. For example, the turtle, and they can block the intestines of the seabird and doing a lot of the ecosystems damage. And so we are worried about these larger particles, but also we are worried about these small particles. So because when they are discarded in the environments, they are under weathering conditions. You expose to the sunlight, you the wave, the wind, they become smaller and smaller. For example, they are, first they become microplastic, then when they are reached to the 5 millimeters, which is that size, we call them microplastics. And then they are continuing to become fragmented and become smaller and smaller when they are reached to the 1 microns, which is even much smaller than the hair of your human hairs, but like 1/100th of your human hairs. Then we call them nanoplastics, okay? So my research area basically following 3 research areas. First, I'm a Lamont, so I'm doing a research on the environmental source, distribution, and behavior. So I studied where they're coming from and how they're transformed in the environments. But my second part was actually collaborating with Mailman School of Public Health, Harvard in the Public Health, to study the health outcomes on that. Basically, I characterizing the exposure to see what actually the regular people get exposed to the pollutants. And then I'm collaborating with this expert in the medical school. They are doing the research to see what kind of disease developed. So that's my major, one of the major research area. My third area is actually engineering solutions. As a researchers, we don't want to just produce a panic. We don't want to just let everyone know there was huge issues, but I also collaborating with engineering school in here at the Columbia, and also with other engineers like SUNY Stony Brook, and we try developing the solutions. For example, we are developing the filter, for the wastewater from the laundry, and also we are developing the method for the collecting the plastic from the rivers and the coastlines, etc. Okay, so that's my major research area. So my first research was starting about 7 years ago with the collaborations with Riverkeeper, because when we realized there was a huge microplastic issues in the waters, we want to see whether they're actually in our New York City waterways. So that's why we go through the collaboration with the Riverkeeper, and John is actually Riverkeeper captain, and he provided a free ride for us. So we, using his weekend time, so we goes there and collecting the water samples, surrounding the Manhattan, and you can see this is the microplastic, there are, concentrations into this, dots, and you can see the higher the dots, that means the higher concentrations. You can see that before they are getting into the New York City waters, they don't have too much, but when they are really comes into the New York City waters, you can see this number increase dramatically. So the highest one is actually in the Newtown Creek, which is we know this is a Superfund site, which is very dirty. And so the question is where coming from. So one of our hypotheses is we know they are coming. We are estimating where they are coming out from the wastewater treatment plants, and we find out there's a huge amount coming out from wastewater treatment plants. So very easy to understanding that it's actually physically or spatially related to the species. For example, this is very close to 125th, they are the North River wastewater treatment plants here, and this is quite close to Newtown Creek wastewater treatment plants. So clearly, when the human activity, when it's close to getting into the urban settings, the human activity causes the trouble of that. Okay, So what I really want to do is to study what is coming out, is how they're affecting human beings. Because we want to need to know that what kind of the particle getting into our body, and if it's getting body, how they get across, get into different of the organs. So that's kind of my research. However, during that time, especially 4 years ago, we don't really have method to identify the microplastics, in nanoparticles. So but particle size is really counts. It matters a lot. For example, do you know the PM 2.5, PM 10? This, this definition. So basically, in the air, if it's particle size more than 10 microns, they will not be able to get into your body, so through your health, until you reach to the below the 10 or below the 10, 2.5. If below 2.5, they even reach to the deeper into your lung. So then, which means the particle size really matters. The smaller the particle, they easily get into the human beings. Can easily goes into the blood, and then goes to the brain, goes to the other organs. So that's why we want to know, to identify method that can work for the nano and the microplastics. And about 4 years ago, I started to look into how we can measure it. Until that time, there was no method. So the reason is because the traditional method, for example, the FTIR and Raman, they can only goes down to 10 microns, or to the, for the Raman it's a little bit lower, they can go to 5 microns. No way you can below the 2.5 microns. So we have a trouble to identify them at the time. So that is, really a bottleneck for us. And then, this is just to give you an example showing, this is a review paper, shows that, all the particles in the publications, what actually the particle size they identify. You can see the lowest that goes to the 23, 23 microns, which means they are even not be able to get into the body. So, so we have the trouble time at the bottleneck on that. So what I did is actually because I want to look into method, so that I go into not only to geoscience literature, but I go to the other like physics, chemistry, and the instrumentation literatures, searching each part, the articles to see what kind of the method we develop, what kind of the instrument we can use. And then I came across this method called stimulated Raman scattering. This method was using the two lasers rather than traditional laser systems. And these two laser systems can stimulate the Raman signals more than 10 million times. So previously using traditional method, you can do the 5 microns. Because you actually increase the sensitivity, now you can go to the nano sizes. So when I find out this method, I was so excited. And then I find out also like coincidentally, the co-inventors of these new technologies is Professor Wiming. He's a professor at the chemistry department at Columbia University. And I was so happy to find out that connections. I sent an email to him. Half an hour later, he replied, said, let's talk, let's collaborating. So that's why we can starting these kind of collaborations about 4 years ago. Through some internal money, we are able to set up the systems. And these systems are basically just showing you how good of this method it is. So, this is basically, we use to call polystyrene, the particles, which is plastic particles. This is the particles 130 and to the 500 nanometers. So 500, 130 nanometers, which is 0.13 microns, which is much in the nano size. And we can clearly see with the increase of the particle size, the signal was increased dramatically also, right? And we can see each individual particles. So this is really give us a lot of hope, because now we can really, previously the invisible world, now we can really see the particles by each individual one, each different type of the particles. So we are so happy about that. And one thing we also find out is very interesting is actually that Raman intensity have a very good relationship with the particle size. This is almost this line, the perfect line there, especially below like 1 microns. And this is actually giving us a lot of the hope. The reason is because in terms of laser, you potentially will not go to even less than 100 nanometers. Now, because this relationship, you don't need to identify the particle by the microscope. You can just, based on the intensity, now you can calculate what actually particle size below like 100 nanometers. So this is really giving us a lot of this, happiness that we can do the job. And so, so after the platform being developed, so there was one question is, what can be the first, case study? What can be the good example for us to do to demonstrating this method works? So we think about this bottled water. The reason the bottled water is because there was already people find out can find microplastics in this bottled water. And so there was a lot of the research already showing that, but no one did the nanoplastics. No one know how much of the nanoparticle is there. And since we already see the microplastics, so the potentially also have a nanoparticle there. The second thing is because the bottled water, when they are making this bottled water, they are using this kind of higher advanced technology to filter the particles out. So if you can really see this in your bottled water, then which means nanoparticles is everywhere. Clearly, it's, really, you can even just see the super clean water, you actually can see that, which means it actually can be in all the environment. So that's why we want to use that as a demonstration. So we select the 3 brand, and we identify each individual one, particles, and then we basically estimating what kind of, what's the concentration. We found out it was about like 240,000 nanoplastics in just 1 liter bottled waters. So it's there. And it was kind of interesting to see, the one thing we are, we see there was, because the system can doing a lot of the measurement of the different type of the plastic, like a polyamide, polypropylene, and a PET. I'm not sure you can see back there, but we also see quite a lot of the PET here, the polyesters. So polyesters, we are now very surprised to see that because the bottle was made by the PET. So you are supposed to see the PET particle there. However, we see quite a lot of the other particles like polyamide, PVCs, polystyrenes. So the question is how, right? So you use the bottled water, when they're making bottled water, they use this super, like a nano, ultra filter to remove the particle already. Why you see these particles also, these different particles in your bottled water? So this is really a surprise to us. So we get a very surprised. So the one question is, we're not quite sure about our results. So we go back, redo the analysis a couple of times. Every time we get the same results. So that is really got us, and we think that must be there. That's the particle there. So the question is, where it coming from, right? So then when we're writing this paper out, we find out that was, this method that used for the filter is called the reverse osmosis. And the materials made this reverse osmosis is polyamide and the PVC and the PS. So, which is ironically means this reverse osmosis actually can remove the majority of particles from the source water. However, they're shedding their particles, nanoparticles into your bottled water. This is really, like a surprise to us. So this is kind of when we, publish this paper, and we get a lot of these kind of interviews from the, media outreach, and there was a very, a lot of questions and a lot of concerns. So one of the big concerns is the tap water safer, right? So yes, with bottled water we have polluted. Is that our tap water every day we use is actually safer? So that's why we come back and then do my students, Kuiping and Giovanna right now is actually collecting the water samples, tap water sample around the United States. And so we get a lot of the samples, and so we are doing the research right now. But what we are really trying to do the first is because of New York City waters. First is because we have like 8.8 million people use the tap water, and we want to test it out. And we know the New York City water, they always claim they are the best water in the United States because they get water from the pristine lakes up in the Catskills, the mountains. So we say, okay, let's try that one. Let's try a lowest one. And then we measure that, the nanoparticles in there. And it was very surprised that we see the other, like a polyamide, poly-PP, and PVC was pretty low. However, we see a much higher, like 2 millions of the just one particle, like a polystyrene particles in the 1 liter of your tap waters. So that is a huge surprise to us. And we don't know how they're getting into the systems. So that's why I was looking into the different of the, the reference to see where this coming from. So I came across this one. This is another report from the Bronx River Alliance. The Bronx River Alliance, they are doing this boom. They're using the boom to collecting the plastic, the waste. And then they are characterizing what kind of waste is coming from. They find out more than, I don't know the number, 73%, you probably will not see, more than, about 73% is styrofoam. So, which means this is all the waste. So 73% of the waste is styrofoam. So styrofoam is very low density. They can floating on the surface, on the rivers. Also, they can be lifted to the air, can deposit from the air depositions as well. So there was a lot of these potentials that are. So that's why I want to talk with New York State, DEPs, and try to see whether we can go and sampling in these remote lakes, and if there was really there, where they're getting into. We could look into their creek and the source water, etc. Right? So that's a lot of the research we still keep going. So that's kind of the continuing research. So so one thing is actually can we use this method to figure out what is actually in our tissue or blood samples. So one of the research we want to see whether these instruments can be precisely to estimating the nanoparticles in our tissue. And we actually use a rat and to expose a rat with polyamide. It's 200 nanometers of the polyamide, particles. And this is the control. This is lung tissue. This is the control, means they are don't exposed to polyamide. But after we expose the polyamide, you can see there was actually in the bronchial, in the venal, and all these kind of small tissue in organs. So clearly, this method can can figure out where in the tissue on using this method. So we are right now collaborating with the other researchers to get the tissue from the from the different patients, and then see what's the relationship with the patient with the microplastic exposure. So another thing we are doing is actually to measure out what's actually in the blood. So this is one of the study. We actually have 2 donors, and we find out that like measure out what actually plastics in these people, and it turns out the 2 people are very different, but one people was showing very high concentrations, like about 14 millions of the PMMA just in their in the blood. And this is kind of very high to us. I don't know where it's coming from, but the PMAA is the material that used for the food containers. So basically, food container potentially can contribute into the nanoparticles into your exposures as well. So as I mentioned, I'm doing the research, but my research was try to see how we can link the exposure to the health. So one of the worry is we know when they are become nanoparticles, they can get into the blood. When they get into the blood, they can go into different organs. For example, we know after you get the exposure from inhalation, from ingestion, they can get in the blood, and then through the blood, they can get the secondary barrier. This secondary barrier is trying to protecting us. For example, the blood-brain barrier protecting us from the particles, any bad material getting into the brain, because brain is the most important organs for yourself. And also we also have the color placenta to preventing the particles getting into the baby side, right? So we want to study more of those things to see whether they can, when they are getting in the blood, are they cross getting into people? The problem of the, like this study is that one thing is that we know when the people getting old, the blood-brain barrier get loose. So that we have junctions, right? You basically have previously being tight. Now, because junction get loose, the particle can easily get transport to the brain side when people getting old. So that's why we are using the fish model. Basically, fish model was when they are, getting old, they have very similar, analogy as the human beings of blood-brain barriers. We want to see compare with adults and also the aged, like a fish, to see their difference, transport, like a rate, etc. So this is one of the research we are doing right now. Okay. So another thing is they can cross placenta. So this is my colleague, Phoebe Stapleton from Rutgers University. She actually used the rat model. This is a rat placenta. And she introduced the particles, nanoparticles from the mother side, and monitoring whatever coming out from the blood here. And then she also collected from the baby side of the blood, and then to see what actually came across. And her research showing just in like 20 minutes, you can see they are, you can see the particles getting into the baby side. And then, you can see the mother side, they actually goes to decrease very fast. However, they didn't go. They are actually getting into the placenta. You can see they are even after like 20, after like 3 hours, you can still see the nanoparticles coming out from the baby side of the blood. So this is really like a demonstration that it can easily cross the placenta, getting into the baby side. The worry is the baby when they're developing their own bodies, they don't really have protections. They don't like human beings. When you get older, you have all this barrier. They don't have barrier when the baby growing up. They just have tissue and cells. And when you have the environments with this kind of nanoparticles inside, then it could be a huge issue. So that's why we are collaborating with the researchers from the Mayo Institute of Public Health using this, like a health and the birth cohort to study more into the, impact on that. Okay. So this is basically what I'm doing the research on the distribution and also the health. But as I mentioned to you, I'm also really interested to see how we can solve the problem. So that is the one problem we are doing is actually we are, we know, the microfibers is a huge, polluters. The reason is because about 36% in the ocean surface waters, about 36% was from the textile, from the washing machines. So this is quite clear. And this number reached to about 70 when you think about when you go to New York City waterways. For example, Newtown Creek, East River, this number reached to about 70. So clearly this is single source contributing a huge amount of the microfibers contaminations. So that's why we want to do the more study to see how we can, remove them. So as you know, when they are in the washing machines, they are getting into the goes to wastewater and then goes to wastewater treatment like sewage, and then they come to the effluent or onto the sludge, right? So and also if you're in the dryers, and then they are going to release it into the air, and then eventually they're also coming down, and people can get exposed as well. So this is a huge issue. So that what we try to do is to developing these filtration techniques. So the filtration, we have this, we got this funding from about 1 year ago from NOAA to do this research, and we basically tried developing these systems. It's innovative, inexpensive, and lower energy and high efficiency filtration systems. And then we actually will stress test in the real situations, like in the laundromat in New York City. And then we are developing the approach for recycle and reuse of collected microplastic nanoparticles. The reason is that most of the research, when they are collected, they don't do anything. They are basically discarded into the environments, again, goes to landfills, etc. But we want to see whether we can reuse it. We don't want to become a huge environmental burden. And also we have the education components and outreach community in that. So this is basically our design philosophy, so that we want to the fashion circular economy. So we know that like a fashion industry give us the clothes, and then we wash it, right? And when we wash it, we collect the laundry wastewater, and then we actually use this filter. This filter was able to filter the water, and so there became the clean water comes out. And this clean water, because they have detergent, we cannot use it. We need to go to sewage. And so, but the filter, the dirty material, was still keeping in this loop inside of your machine. So when there was end up your washings, and then we can load the water back into from here, and then whatever coming loop in there in your systems of dirty materials get into discharge to the sludge. So basically we collected them, and then in the certain times, because we know the problem is that like a filter get clogged. So we want developing a system that can be not easily clogged. So we actually can use backwash mechanisms. So we can introduce the clean water, and then we backwash the filter. So then the filter can be regenerated by itself, rather than you have to replace that for every 3 washes. So that's one of the things we are developing now. Another thing that we are developing is actually we don't want to end up in here. We want the sludge to be taken care. So then we actually, right now, we're developing method to depolymerize it. Basically, we have this fiber we collected. Now we can use that to remake the fibers, or we can cleave into small pieces. And then doing these small pieces, we can reuse these fibers. The materials like monomers or dimers, which is a small repeated unit, we can reuse that and to remake new materials. So that's currently our research on that. So, and then in our tent, which is outside of the geochemistry, common geochemistries, I'm showing you this prototype, and it's this big, and I know that's no one like this one in your home, right? But the reason we do that is because we want a system that we can plug it in, do the test. So very, very convenient for us to the test. When we developing this new technology, when we complete that one, we're going to internalize. Getting smaller can be used in your washing machines, etc. So this is ideal target. Is actually the new target of system. Is first need to be self-cleaning and can regenerate in capacity, because no one will do that. Change the filter or take out the filter to swap the materials after each usage. That became a huge burden for the person who use that, right? So we don't want that. So one the filter can self-cleaning, can regenerate by itself, and also we want basically is low maintenance. So that's why if we can say, okay, every 3 months we have the sensor, and in the sludge, we find out, oh, yeah, that was filled up. Now it's a time to let the person to dump the sludge or give the sludge to us. So basically, we don't want to do that daily, but with like every 3 months, the people can give us a signal, give the signal, and then dump the one. And then at that frequency, probably people can tolerate. If you do it every day, probably they would not be able to tolerate that, right? So the another thing is that we want the system can last 4 years, basically the same life time as the washing machine. So you will not need to be replace that. And so that's another thing we are doing, try to see. And also we want to filter down to the nano sizes, because if it's not a good nano size, then people get exposed to nanoparticles as well. So we want to get that rid of as well. So that's kind of another thing we are trying developing this method is actually should be the high flow rate is high enough to preventing any wastewater from being held back, because the regular washing machine is about 3 to 5 gallons per minute of the discharge rate of the waste, 3 to 5 gallons per minute. And if your system can only take care of 1 gallon per minute, which is much less on the wastewater productions from the wastewater, then you're holding back the wastewater in your like washing machine, may contaminate your clothes as well. So that's why we need this system fast enough to do the work. So currently, we find out those current commercially available products, none works. There was nothing. And we go into the Europe, we do the Asian market, we get whatever the filter there, nothing works. So that right now we are developing a new system, a new filter that are being able to really testing them. Our current calculation is about 15 gallons per minute, which is about 3 to 5 times higher than the required, like flow rate. And so which means we can shrink down the size to be able to match the needed for that. So, and we are testing the 100 microns, 10 microns, and 0.5 microns, and different pore size. And in the future, we want to miniaturize, because no one will like this one putting in your home, right? Especially when you are in New York City apartment. This is probably too big, right? So we want to shrink down the size so that you can internalize this design into your washing machine and use the water and the power systems of the washing machine, so you don't need for anyone to take care of it, just automatically do itself, okay? So this is basically the results showing this is the wastewater without a filter, and you can clearly see filter water was much cleaner. And then we measure what actually in the wastewater from the microfibers. You can see that was much higher, and the filter water with our filter was nothing there. We could not see any particles. So clearly showing this filter works. So this is current research. We try to developing became a smaller size and then do the work. So as I mentioned, we want to recycle and reuse whatever collected from our materials. So that we actually, one thing that we can, as I mentioned, we can remake the fibers from the microfibers. We can connect it and extrude the fibers so that we can reuse that for something like a clothes or carpet, etc. That's the first thing. The second thing is that we want to basically upcycle, because the plastic is so cheap, right? If you just do the plastic fibers, it's going to be difficult to get the benefit from the money, income or whatever you get from that will be much less than you required. So basically, you will not be able to sustainable. So one thing we want to do is could we use these polymers and add more into cost into that, so that can be sold at a higher price. So that's why we are developing method to, they basically cut it into the small piece from the long chain goes to monomers or dimers, so that we can reuse it, and for the higher price. So this is actually in the high school program, and like this summer they did some work and showing that shows that the genetic engineering enzyme doesn't work. The works, but they are very slow. Like it takes like a month really to do the depolymerization, and so our recent research in this summer, we tested of the different type of the metal oxide, and then we tried digesting the PET. We actually find out one of the natural minerals that can be very quickly to digesting these fibers. And within just 3 minutes under the microwave, you can see the plastic disappear. So, and this is natural material, so we don't really need to worry about the environment that much. And also we can regenerating that. So this is really like a hope for us that we can use that, because this is natural material, is relatively cheap, and also can be environment friendly. So that's one of the things we are doing right now. Okay, so I think this is basically like a filter research, and we recently also get funding from the NOAA to doing another like a research that is project. This project, I mean, this is too small for you to see, but I have a larger one in my tent outside of the Commerce buildings. So basically, is we want developing this AI, artificial intelligence, like a device that can monitoring and collecting the plastics. So the thing is that the reason currently the method, you can see this is 4 current method. This is in Bronx River. They use the boom. And this is sea beam that in the Delaware River. This is in the Bay Area. They are using the ocean cleanup using this one. And also this is the Baltimore. You can see the common things is that they are not only collecting plastics, they are also collecting the straws, the leaves, maybe dead fish, dead bird, etc. Right? However, we don't need to collect them. They are good for our ecosystems. And if we collect it, then the downstreams will get less nutrients, right? So it's an interference of your natural system. So that's why we shouldn't collect it. And also another problem is because you getting a lot of them and only like 5 to 10% is plastics. Now you need to moving all these, like materials and sorting out in the land, in the facility, you add a lot of maintenance cost. And so basically, this group in the Baltimore said, I basically cannot sustain because I need a lot of person to do the sorting them out after we collected it. So what we try to do is developing this new method that using the, like a hyperspectral camera and also the regular camera to identify the plastics. So the systems, like of course it's too small for you to see. However, the system is that we have a camera right over here on the up front. The camera will looking in the front and see if there was a larger stuff coming in. For example, the huge branch and tree logs. Then this tree logs stuff will blocking our systems. So then these 2 boomers here will get closed. So they get closed. When there was larger materials, they cannot handle. If there was small enough, then this one would go open. And when there was open, this because the front camera were looking up, say, hey, there was a material comes in, wake up. Then they are starting to wake up. The systems the camera was starting to work, and the GPU, CPU, everything is starting up, being activated by the things. And then we have the camera in here. We're looking down to the bottom of the pantron. This is basically putting on the top of the boat. And then looking down, when they're looking down, they will see, okay, there was a material comes, and they do the scanning. And then they are figured out whether that's plastics or the dead fish or leaves, etc. And if it's really, like it's dead fish or trees, then this one, they get here, they're not going to open. So they let the whole, like dead fish, tree, leaves, whatever, coming down back to the mainstreams. However, when we say, oh, this is the plastics, now this one will close to this direction. So then the plastics and also all the materials will get into this trash bag here. So the systems will be smart enough to do that and also tweeting the data to us to let us know, oh, there was a lot of the plastic comes in or etc. And also, we also have a camera in here so looking into this, trash, like a bag, and then see if it's full. You are tweeting us, let us know, we go and then grab it. So that basically is this system we're going to putting into we just got funded from the NOAA. So the next 3 years we're developing this new technologies in here. So yeah, this is basically my summary. I take too much time, sorry about that. So yeah. So the first thing is that we did find out the wide distributions of microplastics in New York City waters. We need for the control and the removal efforts. And so also we're developing advanced Raman techniques to measure nanoplastics. which basically opens a window to this invisible world before, because previously we don't know whether they are there. Now this new technology is helping us to know they are there and how much, what kind of material is there. So that's a breakthrough, huge breakthrough. And also we find out nanoparticles are abounding in bottled water and tap water, and we are right now developing the, systems, a filtering system to remove them from drinking waters. We're also developing a fast and a low maintenance filter to preventing the leakage of microfibers and nanoparticles into the water. And we are developing this smart plastic monitoring collection system that developing in the next 3 years in some of the Bronx River, etc. So thank you very much for your attention. I take too much time. Sorry about that.
Thanks, Beizhan. We're moving from out of sight, out of mind to out of sight, top of mind with this sort of stuff. We have time for a few questions. Some of my colleagues will have microphones. Please use them.
Yes, please. So you tested, and then the New York water, the tap water, there was PS. Did you test the Catskills to see if that also had PS, or it came further down the system? Is it coming through rainwater? Where does this PS come from?
So that's a great question. First thing is that we just found the results like 2 months ago. We haven't got a chance to look at it. However, the thing is that the New York Department, DEP, they think the water is so clean, they even didn't use any filter. So basically, what coming out from the tap water was actually in the Catskill, the reservoirs. That's our understanding. So because they didn't use any filter to remove it, they just used UV to kill the bacteria, but they didn't do anything to remove the particles. So we think that's coming from the reservoirs. And there was, in the reservoirs, surrounding the reservoirs, there was a lot of this kind of the neighbors, like towns. They are doing quite a lot of the festivals in the summertime. So they are probably, burning things and doing the music in the festivals, a lot of things, there are activity there. So we think potentially coming out from those activities. But it's a great, my students, Huiping is applied, NSF project, and so we want to do more research on that. Because we really want to solve the problem to see, because this is affecting 8.8 million people in New York City.
So is the city going to put in filters then?
We haven't talked with them yet. This is the first time that everyone listen. This is the first time. We haven't published the paper because we want to, first we want to do the experiments, repeated the experiments. Because in New York City, there was 3 types of the waters, right? 3 sources. One is the Catskill, one is Courland reservoirs, one is the groundwater, right? So we want to compare these 3 different water sources and figure out there are different types of the plastic, etc. And then we're going to talk with them to see whether they're allowing us to go to the reservoir to collect the samples to see what's the resource, where they're coming from. However, sometimes it's difficult to working with them, yeah.
Water filter adequate to remove nanoplastics from our drinking water?
So yes or no? Right, so if they are in the source water, the home filters, if they go down to the nanometer size, they can remove the particles from the source water. However, they're potentially shedding the particles into your water because they're made by the plastics. So many of the plastics was made by, for example, reverse osmosis. That's why I said the polystyrene, and also why the polyamide we see a huge amount is because they are reverse osmosis filter was made by the polyamide. So they are they are filtered water, plastic from the source water. However, they are contributing, they're shedding the nanoparticles into the water you create. So we are developing the method using the stainless steel and the ceramic, the filters, so that we can plug it into your tap water, so then there was no worry about that anymore. This is currently, we are developing this method, but I didn't presenting anything because that's kind of the patent protected and many other things, doing. But we are developing that one. Hopefully in 1 year or 2 years, we should be able to, developing this method, commercialized, so everyone can have clean water to drink. Yeah, go ahead.
the dolphins had plastic in their breath.
Right.
So, I mean, have we reached a point where it's impossible to do anything? For example, it's omnipresent in the oceans. There's no way to get microplastics and nanoplastics out of the ocean. Are we doomed?
Yes, this is the method. This is the method I'm doing. Because most of the plastic was from the land. We actually polluted ourselves. We get into the river, get in the lakes, goes into the oceans. So that's why we collect, because the larger particles, they're getting into the ocean, they became smaller and smaller, became microplastic nanoparticles. What we are doing is developing this method, putting into the oceans, or the rivers or coastline, automatically collecting the plastics rather than let them go into the ocean. So that's kind of the effort we are doing right now.
One more question.
Yeah, go ahead.
So recently people have become concerned about PFAS chemicals.
Mm-hmm.
And is there a way to detect PFAS chemicals? And what happens if people ingest nanoparticles that perfuse PFAS in their systems?
So we do find out, especially for certain, like clothes, for example, like a raincoat, and they are made by the, like the polyester, ester, and also something other plastics, but also they are coating with the PFAS. So what do we try to do to see whether our filter was co-benefit for the remove the PFAS as well? So that's one of the things right now we are trying to test it out in our systems. However, PFAS is very, very difficult to chemicals. They're called forever chemicals. The power reason is because, in the Earth's surface, there was no way to, basically, remove them. And because they are such a strong chemical bonds, they are kind of difficult to under even sunlight, because you don't have a UVC on the, because UVC being like filtered by the ozone. So in the systems on our surface, we don't have a UVC. We cannot break it into small pieces. So that's why we call it forever chemicals. So that it's currently that was developing the method using something like filters, some filters. I know that one of the professors at the Columbia Engineering School, environment engineering, he's developing some of the new technology to remove the PFAS. And I'm collaborating with them to see whether we can do these two things together, to just saving everyone's, time and efforts. Yeah. Thank you very much.
Thanks, Beizhan. Just another lesson that we're downstream or downwind of everything that we do. But it's not a doom scenario, however. We're working on this in many fronts to try to see what we can do both at the source and both downstream and downwind. Much to learn about this. But let's thank Beizhan once again. We are going to have another talk. I should mention that if you enjoyed a talk like this, or if you are bothered by the doomsaying in a talk like this, we're going to have a series of public lectures. The next one will be the evening of November 13th. I think that will be about extreme events, hurricanes, and so on. So thank you again.
So my tent is outside of the Commerce buildings. And if you try to know more details, just go visit my tent outside of the, Commerce buildings.
Can you put it down here?
Yeah, I put it down here. I think this is probably my lunch.
Oh, yeah. There you go.
Hi. Okay. Thank you. Right, right. Oh, okay. 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 Yeah, sure. So how far away from your place to here? Like your school here? University. Okay. Yeah. How can we see what kind of? Because we cover quite a lot of things.
I mean, I went through them, they looked okay.
Oh, okay.
See, this is the one right behind, that's Jacob.
So Jacob, me, and Einat.
Here's yours.
Okay.
I went past it.
Oh.
This is right behind his. This is your first slide.
Okay.
This is, you want to go through yours?
Yes, yes. Okay. Oh, come on. It's gonna move faster. There's a video. Oh, there you go. So that is a video. How can I?
Maybe it didn't make it through when it was transferred.
Okay. Oh, it's playing.
Okay. Oh, okay.
Okay. But it's no
I guess
sound,
you-
right?
Oh, I have to turn on. Maybe I have to turn on the sound.
Okay. Oh, I think it's on actually. It.
No.
Click. Okay. How can I project again?
What do you want to do? Oh, save your work. Make sure you saved any changes you made.
Okay.
And then start from current slide.
Where's that?
Give it a second to save. Because this thing
Oh,
is
yeah, I guess you've
huge.
tapped all of them. Okay. Slideshow. Let's see. All right, perfect. And this. Oh no. And okay, and this. Uh-oh. I see. There's something weird with that slide.
What are you trying to do?
So this, is there an animation panel? I use Windows, so.
What are you trying to do?
I want to see the sequence of animations. There should be a panel, a link there that pulls up a panel. No, exit is. So if you click that, yeah, it's supposed to allow me to press the click to make it stop playing, but it's okay. What I would
If
do,
you click on it, it'll start, and then click on it again, it'll stop.
okay, let me just review again, and then how did
Play.
you
Play from under slideshow.
Oh.
And then play from current slide.
Okay. Okay.
And
Can
then-
I need this one to show first before this. I'm sorry. This is animation. This is so strange. It's supposed to allow me to remove animation or. Okay. No worries. I'll figure out a way to just say that. Oh, that's the thing, animation pane. Oh, finally. Exactly. So this games, I guess it's that picture. So this is why. Wish it's highlighting. This one comes first. This is 3. I want 3 to be here. There you go.
I'm able to save.
Save. All right, we're good now. Thank you.
Okay. Oh, no problem. We'll look. Okay, let's look at yours. This is your first one?
No, I'm the very first one.
Oh,
so I'll
sorry.
be at the top
Yeah,
of
yeah,
the-
yeah, yeah.
I think it should just that very first video. Oh yeah, go down, sorry. This one. We just want to check it's muted. Yeah, that's fine. No worries. So we can just go from there. Yeah.
Okay, so it starts here, then there's this slide, then there's this one with your name on it. Cool. Okay.
No worries.
Oh, and we have the slide advancer, forward, back. No problem.
You have uranium, very highly enriched uranium, and hydrogen goes through heat, and then hydrogen goes back into the forward back.
And we have this microphone system, so we can
You can walk around and you can, it's meant to work.
Oh, cool. But there might be feedback.
Oh, no, that's why everything you do. When you go behind the podium, and when you're done and you go away from the next, well, you're the last one, so then I'll meet you when I got it.
If you want your color, the chemical reactor, yeah, all of it. So the oxygen is probably much more. And then most of the rock is fuel. To clean out the earth is much bigger than you get the chemical rock just with one. You barely work as it. Because you 1.5 times twice the gravity. You know, so when a colleague I had worked, one of the, well, it has to be, you have H2O, so you form water, where you burn hydrogen and oxygen. And what we make water is hydrocarbons or any hydrocarbon. When you burn it, you can't. But if you put it with water, it's really extreme. H2O equals all of the oxygen. Yes. So you're going to carry maybe oxygen. That's what we're talking about when you do it. People have been talking that for a long time. So I had this colleague years ago, a number of years ago, and he didn't believe in music. So he didn't believe this, and so I was trying to tell him, it's so far away, it just seems like there's no way to get there. And, you know, I think I told you. Yeah. So I tried to tell him, you know, mostly, it's mostly, you know, it's like, and then the question is always, why did we continue doing it? That's an economic decision. That, you say it took 5% of GDP. That's over, you know, like 12 years. 5% per year over 12. No, not 5% per. 5% over. Maybe 4% of the federal budget or something. But it was a huge amount of resources. 400,000 people. Maybe it was 4%. That's because they hand-built everything. But it was about 5. Everything that had to be done with paper. You know, computer models. It was almost about a decade. Nowadays, there's a chance to bank things together with computer models. Well, that's where SpaceX comes in. We must have developed everything from scratch. No, he used a lot of the standard things. I know he developed a lot of the basic ideas. Yeah, but people have done it all before. So it's not like from Apollo, they had developed stuff and research from the beginning. They had enough. They did a lot of first, like he used liquid oxygen. But Musk just used standard methodologies. And they added technology to it. But liquid oxygen, liquid hydrogen, and he used liquid nitrogen. They used kerosene. There's pros and cons. There's rockets and things. He's the first one. Out of oxygen. My point only is, I was trying to make a point, 2 points. One is an economics issue. The reason it didn't happen is this. Nixon said, oh, we're cutting that. We're not even going to do an Apollo 17. Or 18. 18, they didn't do an Apollo 18.
Welcome, everyone. Hi. Well, we're coming up to the last lecture of the day in our open house 2024. I hope you've been having a good time outside. Gorgeous day. Make sure you see all the exhibits and so on. There's a lot going on. This happens to be our 75th anniversary year for the observatory. We were founded in 1949 by Doc Ewing, and one of the glorious parts of being in earth science is that you actually have a chance to check your hypotheses out in the field. We go out and we explore the oceans, we explore the land, we explore the atmosphere, and in that way we're sort of testing what we think we know about the planet. And it's just a fantastic part of what we do here. There's also a flip side to that, in that sometimes you have to go out into the field and look at things to try to formulate what your hypotheses actually are. In other words, the planet is teaching us. And one of the attractions of being a field scientist is just that. Not only are you going out checking what your preformed hypotheses might be, but you're looking for clues for something new that might actually tell you what the planet is all about in ways that you hadn't even thought about before. And we're trying to capture that around in various exhibits and so on. So we're very pleased to present to you today just a very small slice of the sort of field work that we're all about. And I'm being joined by three of my colleagues, Jacob Anderson, Einat Lev, and Folarin Kolawole, who have essentially designed their science to be field workers. So I think we're starting with Jacob. Is that right? Okay. Please welcome Jacob to the podium.
Thanks, Art. Okay. Thanks for spending the next half an hour or so inside. I know it's a beautiful day out there. Okay. So for the next 10 minutes or so, I'm going to take you on a field trip to northern Greenland. This is where we were doing our field work in August this year. This is a view flying up Victoria Fjord with a bit of a cloud ceiling, but nonetheless a spectacular place to do field work. My work at Lamont is part of a bigger team. This is just a small part of the Lamont component of the team across a number of universities in the States. And we're looking at the sensitivity of the Greenland ice sheet. And we're looking at this from a few different angles. One is peering beneath the bedrock and looking at signs of retreat in the past where the ice is smaller than today. And we're also looking on the margins to look at how the ice has fluctuated on the edge. So I'm going to be talking a little bit more about the margin today, but you can learn more about the Green Drill project at the tent just on the lawn down the hill here as well. If you haven't already, there's a whole heap of great ice and paleoclimate activities there. Okay, so Greenland. I've got a model here of the Greenland ice sheet, and there's a few of these too that you can look at. If we take the ice off, there's landmass underneath Greenland. And if we melted all of that ice, it would be about 24 feet. So it's quite a lot of ice that Greenland is locking up in sea level. But the questions are, how sensitive are different parts of the Greenland ice sheet? Where is it more vulnerable? So the questions we're really trying to understand are, which parts of Greenland are most sensitive to change? How has that happened in the past, and where may that happen in the future? So in August, we went to North Greenland. This is a picture here on the margin of the North Greenland ice sheet. To get there, we flew from Svalbard in this top right of the map here to a Danish military base, Station Nord, and then from there we then went to Victoria Fjord. So this is one of the most remote places on the planet, incredibly difficult to get to and logistically really challenging just to even get into the field, let alone to start doing any field work. The reason we were really interested in this part of Greenland is because these are a number of samples that have been collected similar to what we're doing. But you can see there's this huge gap in northern Greenland. So we're really trying to understand this part of the ice sheet because it's so remote and we don't have a good understanding about how northern Greenland is behaving. And if you look at this image here, you can see this black line is the the extent of Greenland during the last glacial period. How big was Greenland during the last glacial period? It was extended out towards the continental shelf alongside huge parts of Canada and North America, where you see New York. In fact, Central Park was also covered by ice during the last glacial period and has subsequently retreated. So what we're really interested in here was how quickly did the expanded Greenland ice sheet retreat from that last glacial period to the modern position where it is today. So how do we get there? We fly in this R66 Robinson helicopter. We couldn't fit all of our gear into this helicopter in one trip, so it did require multiple trips shuttling humans and gear to get out into the field. And this was our team, a team of 4 geologists, so 3 from Lamont and 1 from the US Geological Survey. And so we were camped out on the edge of the ice sheet for several weeks in August. This was home. This was our home for a few weeks. This is our living tent, or our kitchen, where we would have breakfast in the morning, get equipment ready, and then have dinner and unwind in the evenings as well. And then our sleeping tents just off in the distance. So this was a very nice, cozy tent. This is what it looked like inside. Often people say, oh, you know, what did you eat? Were you eating a lot of dehydrated food? No, but because temperatures were above freezing, we only could take non-perishable food. So a lot of canned beans for burritos, this kind of thing, and also a lot of Spam, which if you fry it up and get it crispy, it's actually not too bad. So a lot of pastas with fried Spam. You get very creative in the field when you've only got a few options available. But yeah, so this was a typical evening for us cooking after a hard day's work, and nice to have a nice warm meal. It wasn't always pretty. I'm going to show a lot of pretty pictures, but it wasn't always like that. So obviously there were some challenges when you've got very low visibility and it does get cold. Fortunately, we didn't have a lot of wind, so that was one advantage. It was cold, but it wasn't too windy. So that really does make a big difference when you're working outside. Okay, so what were we doing? We're using a technique called cosmogenic exposure dating. And so on Earth, we're constantly being bombarded by cosmic rays. So this process happens when you may have heard of supernova explosions. So stars from the Milky Way, when they explode, they emit these particles. And then when they interact with the upper atmosphere of the Earth, we get this secondary shower of particles. And then from these secondary cosmic rays, they then interact with minerals and rocks. And so this reaction that occurs within the rocks changes the chemical composition of the rock, and you can start to accumulate what are called cosmogenic nuclides. And so you can liken this a little bit to like a suntan. So when an ice sheet retreats and it deposits a rock, the surface of that rock becomes exposed, and it starts to get bombarded by these cosmic rays. And then over time, the amount of cosmic rays, the amount of exposure that rock has had changes the accumulation of the cosmogenic nuclides. So like a sunburn, if you spend too much time in the sun, you can get a greater dose of radiation. And then if you go out of the sun, that repairs or recovers. And so a similar thing can happen if ice was to re-advance. That exposure history changes as well, because the rock surface is no longer getting dosed with this cosmic radiation. And so we're looking for these surfaces that have been exposed by ice, exposed since the ice has retreated. So what does that look like? Well, we're walking around these landscapes looking for nice deposits that demonstrate that they've been emplaced by ice, and then that ice has subsequently retreated. So we're walking around the margins of these landscapes looking for landforms that can tell us this story. So that looks like these nice boulders perched on smooth bedrock. This is just a normal sort of power hand saw to collect the surface, the upper few centimeters of the surface that we can then take to get our surface exposure history. We're also interested in bedrock, so the boulders in place on top of the bedrock and the bedrock itself. So as that ice advances, it polishes and it smooths the bedrock, and then as it retreats, it leaves these nice, beautiful surfaces that we can sample to get an exposure history of the bedrock. As well as those surface histories, we can also go drill into the bedrock itself and go deeper in time and collect these bedrock cores. And these bedrock cores allow us to understand long-term climate history. So as I was saying before, as the ice advances and retreats, it changes the chemical composition of that signature in the rock. And so we can look at the overall exposure and burial history by looking at these deeper bedrock cores. And you can see this was on one of the colder days. We decided it was a good day to drill, it was the water was freezing, and it was a bit challenging to drill, but we managed to get a core that is 4.8 meters long. So drilling right down through that bedrock, 4.8 meters. The photos I've just shown are from close to the modern margin, but we also wanted to understand the entire history of the fjord. So we went out towards the coast. All of that ice in the back of this image is actually broken up icebergs, but there's so much of it that it's kind of just this melange of ice. So that's right by the coast there. And so again, we were collecting these samples that had been deposited as the ice had retreated up the fjord. We then took a helicopter further up the fjord to this enormous moraine. So these moraines are basically rock material that's been transported by the ice and then deposited there, and then as the ice has retreated, it's left this huge, this goes for miles along this ridge here, these huge deposits. So we were, again, collecting these boulders right on the crest of this moraine to get a really nice age constraint of the timing of when that moraine was deposited, and that allows us to understand how the ice had retreated from that position. From there, we then went even further out to the Arctic Ocean. So this is 82 degrees north latitude. This is the Arctic Ocean in front of us, Victoria Fjord on the right of the image here. So we've gone all the way right out to the coast. And so these samples that we've collected give us a retreat history from the coastline all the way up the fjord to the modern ice margin. So we're able to reconstruct how quickly that ice has retreated over time, and then use that information and these rates of change and compare them with contemporary rates of retreat to give us some perspective around how quickly ice has been changing. Now, a lot of people always ask me, did we see any polar bears? No, we didn't. But we did see a Greenland wolf, which was very interesting, actually. It's a subspecies of the grey wolf. So one of the days when we were walking up to the modern ice margin, we saw these tracks, and then as we went further up to the ice, we saw this wolf at about 500 meters elevation, which was very interesting and unexpected. And I think we were as surprised as the wolf was to see anybody there. We also saw muskox and hares and a few other species, but fortunately, I think people say, "Oh, did you see a polar bear?" The good news is we didn't see one, because that could have been a problem. And so once we'd collected all of these samples, we then ended up, the helicopter dropped us off at another site, and then we spent a few days waiting out there for the weather to clear, and then this Norland Air twin-otter plane picked us up with all of our gear, and then we went back to Station Nord, and then from Station Nord we then travelled back home from Iceland. Yeah, thank you very much, and I hope you've enjoyed this trip to northern Greenland.
Hi everyone, my name is Folarin Kolawole, you can call me Fola, and today I'll be taking you back to the tropics, so closer to the equator. So good job, Jake. All right, there you go. So my research for about a decade now in the US through grad school in the industry and back in academia as a professor here at Columbia has been addressing a particular science question, which is how do tectonic plate boundaries initiate? How do they start? So we know that the outermost shell of our planet has been undergoing recycling for about 4.5 billion years, okay? And this recycling involves splitting apart of tectonic plates, of continents splitting apart, and you have upwelling of mantle materials creating new crust, which we have underneath the oceans, called that oceanic crust. And we also know there are plate boundaries where tectonic plates are essentially colliding against each other, in which, depending on the density contrast, you can have one plate shoved down underneath the less dense plate, in which that entire continent or oceanic crust disappears, gets consumed in the mantle. And we also have plate boundaries where the plates are shifting laterally along the boundary, side by side. So an example of this will be the San Andreas Fault, onshore, where we have them onshore in western US, California. And here, an example of this happening in present day will be the Marianas Trench or Aleutian Trench in the Pacific Ocean. And examples of convergent plate boundaries where density contrast does not allow one plate to subduct under the other, but because of similarity in contrast, both plates collide and they create mountain belts, they crumple and create big mountain belts. An ancient example would literally be the Appalachian Mountains right next to us, or the Rockies, all right? But in present day, we actually have this happening in the Himalayas. Right now, it's been colliding for millions of years and it's still happening, all right? But the part of this science question that I care most about is how divergent plate boundaries initiate, because each one of this is essentially very complex, all right? You would imagine that the initiation of divergent plate boundaries should be a simple thing. You just pull it and the faults just appear and the continent breaks. Oh no, breakup is difficult. Okay, that's a joke, all right? All right, so I've been, essentially, as a scientist, if I wanna investigate how plate boundaries initiate, I shouldn't go to areas where the plate boundaries are already mature. The reason is because the early stages of the process, the structures and rocks and deformation that are often in place in the early stages of the process become overprinted by later processes. So essentially, it can be challenging, piecing apart structures and inferring processes that might be primarily dominant in the early stages of the process than in the later stages. So essentially, you want to go to a place where the system is just starting. And we have two spectacular areas on Earth where this can be explored. The one that I think is the best and most enigmatic, and I think a lot of people would agree with me, is actually here in East Africa, right there. The East African, we call it the East African Rift System. Some people call it the Great Rift Valley. It literally snakes around, through the continent, and I'm going to show you a more detailed map in the next slide. The other area we have been looking at this is Western US, so right there, essentially an area east of the San Andreas Fault, which we call Eastern California Shear Zone or Walker Lane. So if you're familiar with Death Valley is literally sitting within this zone. It's stretching apart. Okay, in these locations, I'm primarily trying to understand processes that are associated with the initiation of the plate boundary and could potentially lead to successful continental breakup, because we know that these plate boundaries do not always succeed in breakup. Sometimes they fail. For example, the mid-continent rift of the US failed, right? So we know they can fail. But understanding the processes that drive successful plate divergence is very essential if you want to understand how our planet has come to be what it is today. If you Google East African rifting or splitting, you would likely see a picture that looks like this, essentially an artist's depiction of what they think East Africa would look like in the future if the continent successfully break up, like that. All right, so I'm going to show you a few photos from my, many field work in East Africa, but these photos I want to show you on this slide will basically demonstrate how different the morphology of the surface looks like as you go from north to south along the rift system. So this map, showing a map of Africa, the red dots are earthquakes. So essentially, if you just look at this earthquake, and this is from USGS earthquake catalog, because they have a compilation of earthquakes across the world. The clusters of the earthquakes basically show you the traces of the divergent plate boundary that's initiating. Each of those earthquakes are breaking on faults that are slipping down slipping down across the fault plane, allowing the stretching of the continent. But the cool thing about East African Rift System is that in the northernmost tip of the rift system, that part of the plate boundary is essentially undergoing transition to breakup. So if you want to understand processes that drive successful breakup at the later stages, that is where you want to go. And if you want to look at intermediate stages of rifting, of basically plate divergence, you want to focus on basins that are within this part of the continent or part of the system. And if you want to understand how the system really starts, you want to go here, right in the southern part of the continent, in Okavango, northern Botswana. So I'm going to show you photos first from this part, and you see what the surface topography looks like, and then I'll take you south. All right, let's go. So this is from a rift basin called the Albertine Rift in Uganda. It's located right there. And this is showing one side of the Rift Valley, one boundary of the Rift Valley. So you see that mountain up there is basically one side of the fault that is slipping up. And we are standing here on the other side that is slipping down. You can see how flat it looks. All right, so essentially, when I go out to the field, I want to target the base of that mountain and, if I'm lucky, find an exposure of the principal slip surface of that fault and look at what the characteristics look like. How pulverized are the materials? Do I see evidence of fluids that might be weakening and softening the rocks? Do I want to see evidence of past earthquakes? If I'm lucky, that could help me understand how this fault had been behaving in the past relative to how it might be behaving today. Does this fault pose hazards to the people living in this region? Are there lessons we can learn about divergent plate boundary faults of this size here that we can take to other parts of the earth, like Western US, Death Valley, to forecast earthquake hazards on the border fault of Death Valley? That's literally how we think about these problems. So this is showing a photo of a volcano in the southern part of this basin. So essentially you see in the background, there's a mountain there. It's literally stacks of volcanic craters sitting right on the southern continuation of this fault. That basically tells you that there must be some relationship between this fault and the localization of volcanoes there. Essentially, we know that faults are cracks, and they allow ascent of melt, magma through the crust. So in my stand here, my students basically show sandbox experiments of stretching, and they have a rock where you have fault planes within the rock, and if you look at the fault planes, that's where you see lenses of mineralization within the rock. You don't see the mineralization on the sides of the cracks themselves. They're literally within the cracks. So this is one of the observations that drive how people go to the field, deploy geophysical instruments, and look for evidences of magmatic ascents in the field, in rift basins. So if we go a little bit south, you see that this is in southern Malawi right there. You see the same morphology. Flat basin, it's subsiding. You can have lakes, you have swamps, you have all of that here because rivers flow downstream. It's humid because the uplift of that mountain changes atmospheric circulations locally. It creates wet conditions up in the mountain. So you see all these rivers taking sediments into the basins. But if you come towards the southern tip of the system here in Okavango, that's what it looks like. And it's actually a desert. So we cannot say, oh, the sediments are coming at such a high rate, so they just fill up the whole valley. That's why you really don't have that topographic gradient. No, it's a desert. So the sediment flux is way lower than what you have here. But the key point is that if you look at the thickness of the sediment that I've accumulated here above the subsided basement, it's only 700 meters in comparison to here where we have 5 kilometers. We know that because we have a lot of geophysical images and boreholes that have gone down these basins. So this is a place I want to go to if I want to understand how rifts are just starting. Okay, in the next few slides, I'm going to take you through journey of my field work where I was actually going out to the field to address a specific science question. And I'll show you a map of my plan, and then I will show you what I was successfully able to accomplish. Keep in mind, this vegetation you see here is going to be a big challenge. I would have wished that the climate here is the same as what I have here, basically a desert here, just so that I can see more exposures of rocks. So when I go out to East Africa, I'm basically trying to figure out how to up my luck in finding exposures of the slip surface of this fault, right where I can easily get to it without going too far from the roads, or even if I have to go far from the road, as long as I'm going to be lucky finding it. Not like I hike 2 miles, get there, and it's all dirt and forest and bush, and I cannot see anything. Okay, so I will show you a map of my plan of where I think I might be lucky to find these things, and then when I get to the field, you know, cases where I'm lucky and where I'm not. All right, yeah, so this is just a zoom in, like a photo showing what that is like, just like a little blip in the topography. That's the fault trace right there at the base. Okay, so this is showing a map of a basin called the Tinah Basin in southwest Tanzania along the East African Rift System. And it's a topographic map, so you can imagine that the flatter areas are, represent the middle of the basin that is going down, subsiding. And the rougher patches represent uplifting blocks on both sides of the Rift Valley. And that sharp break you see there represents the trace of the basin-bounding fault. That is the principal play boundary fault. They are the biggest fault. They are the fault that extend down into the mantle. And if we can understand the behavior of this fault, we can get a sense of how the rift is evolving. Okay, so that was basically our plan for going to the field. This was actually this last July, this field work that we had this last July, myself and one of my PhD students. We had many pins placed, and these are locations where there are roads running straight across the fault, where we think there might be road cut, or there's a town there, or a river channel that's really close to the main road, where we think we can easily get to it and see exposures, hopefully not weathered. And this is basically showing what we were able to get, like sites where we're actually able to see exposure of the principal slip surface of the fault, providing some insight into how these faults are evolving. And I'm going to show you photos from both sides, so you can see some cutting-edge new results coming out from our work in East Africa. All right, so right there, this is a drone, an image from my drone, and that's the road right there. You see this, essentially here, you see flat topography. That's the basin subsiding. And here, you start going into the uplifted mountain block. And the contact is this scarp right here, right by the road. This is the dream. This is our dream. Like, oh, great. Now I can collect samples. I can do, if I see an offset soil layer, I can do cosmogenic dating or OSL dating, some of the techniques that Jake described. I can do whatever I want when I see this exposures. I can collect samples. I can put timing on this fault when it's initiated. I can estimate how fast the fault is slipping, and I can compare that with other faults around it that I have exposures of and see which one might be causing more earthquake, which one might actually lead to the breakup of the continent or not. This is really what we're looking for. Okay. Right here, you see this polished surface is the classic expression of a principal slip surface of a fault in the field. We actually have one like this close by in Suffern, which is the exposure of the Ramapo fault, which was active 230 million years ago. It was the principal plate boundary fault here in New York, New Jersey area 230 million years ago. Just no more active now because the continent broke up. But this is active. This fault is actively slipping. There are earthquakes all over this area that's been recorded and published on by other scientists. But there's been no study here showing what the exposure of the fault actually looks like or what we can glean from that. Okay? So as a structural geologist, I just don't want to see the slip surface. I want to see striations like that, which can tell me how this fault has been slipping. Is this slipping laterally like that, strike slip, or like that? Because depending on the sense of motion, it can tell us something about how it's evolving towards breakup. Okay, at this other site, we even got luckier. Someone had already dug a quarry there, and in that quarry, so essentially again, flat basin, uplifting mountain, right in that quarry, this is what you see. So I'm taking this shot from this direction, okay? So essentially, we expect the fault trace to go that way, right? And right here, nature did it for us. You have that gully right there, cutting right across where we expect to see the fault trace. So I'm going to show you what it looks like. It's actually really, really exciting. All right, so that's what the exposure looks like. And that is me crouching and trying to understand the nature of the deformation in the rocks, because we can see clearly that this is colluvium. It's basically just dirt running down from the top of a mountain. They're often composed of jumbled mess, all right? And this old material here, the red colored stuff is clayey, we call it gouge. It's basically highly pulverized materials that's been compacted along the fault zone. And right behind that, what you have is fractured rocks like this, which we call breccia. But the cool thing is within this breccia, there's the band there that's really exciting. So that whitish layer right there, so you see all the fractured stuff. That whitish layer, if you look closely, we have surfaces cutting through it that have striations on them. Sorry, the picture is not perfect here because of the projector. But you basically have that, which is what I want to see. It's a small, teeny tiny, I mean, that's torch for scale. That's a teeny tiny exposure of what we saw on the big slab in the previous slide. I will still take this over nothing, okay? But better still, there's something cool that we actually found in this outcrop. It's these dark bands of what looks like veins running through the rocks. There's even better examples here. They're slightly grayish. Sometimes they look black where you see them. This is what we call pseudotachyllites. Pseudotachyllites are the real golden class geological record of earthquakes on faults. They are very unstable at the surface. They weather easily. They are rare to find on faults. If you find pseudotachyllites, that is, oh yes, you can say this fault has ruptured earthquakes at this segment in the past. Because we know faults have locking segments, slipping segments, there are all kinds of complexity of movement over the life of a fault. So this is really spectacular. This is actually the first time that we are observing pseudotachyllites on exposures of fault along the East African Rift System. This system has been studied for decades. This is the first time I was so excited. Okay, I will move on and show you this other, some photos, a video, and we'll call it, I'll finish it. All right. So now I'm taking you to Okavango, where we don't have a lot of slip on the fault, where we can imagine that it will even be more difficult to find exposures of the principal slip surface of the play boundary. But sometimes we get lucky. Some landowners in northern Botswana have dug a quarry on their land because they thought they might find copper, and they didn't find it, so they just left the hole right there, and I was lucky that they gave me access to the land. I found that on Google Earth, again, when planning my pins, putting pins. And then I went there, started asking people around the small town nearby, do you know the owner of this land? And they were able to connect me to the owner of the land. And it was like, oh yeah, go do whatever you want. Let me know what you find, all right. So essentially that quarry has an exposure of a fault. But the cool thing is if you go into that quarry and you look at that part of the quarry, what you see. So there's a nice fault there. It's not a big fault, but the rocks around it record a very important feature. Essentially, this is what we call hydrothermal breccia. It's basically blasting of rocks under high pressure due to trapping and sudden release of hot fluids. So if some of you heard about the recent hydrothermal explosion in Yellowstone National Park, this was exactly what happened there. So this has now been uplifted and exposed due to faulting activity and uplift around the rift, this incipient young rift. But what you see here are big blocks of rocks that have been blasted, and in between them you see precipitated minerals from fluids that were flowing through. All right, and that's just what these photos are showing. And you can see crumpled rocks along the slip plane on that fault. So essentially, these are the blasted rocks, and we can even detect the sense of flow of the hydrothermal fluids and map it across the entire outcrop, along the entire quarry. And this is showing again striations, confirming that that plane is indeed a sliding plane of fault. All right. And one of the things that someone like me like to do in the field is to, I hope it's played. Oh, I was hoping that would play. Anyway, I'll move on. Is that when I see exposures like that, I collect samples because I want to date the calcite. I want to date the mineral that precipitated from the fluids to pinpoint when that fluid ascent happened. Did that fluid, the hydrothermal breccia event, did it happen recently, assisting the initiation of the play boundary? Or did it happen millions of years ago way before the current rifting started, such that the rift is exploiting this play boundary? These are frontier areas of research on divergent play boundary initiation that we do not have answers to yet. But here I have a video showing how heavy my so my field, my local collaborator is a lecturer in Botswana, was actually recording me as I was loading up my bag with samples of this rock. And I wanted to lift it up, and I was like, oh, yeah. So, yeah, that was the video I was going to show you. Anyway, finally, there are times when we're unlucky. So this is showing another exposure or a scarp, along this boundary faults. It's just a little blip in topography like that. So we're going to run a shallow geophysical imaging across this fault to see how displaced the sediments are along this fault. And we had a serious problem doing that because of this. And we had to leave, so we didn't get any data here. So I'm just going to do this real quick. Click. Don't run away. That's an elephant. The elephant is running away. You're going to see what the elephant did, so we had to run. Oh, no. So essentially, the fault line was on what they call the corridor, elephant corridor. Oh, no. And elephants are pretty smart. They remember because they only go along the corridor, they don't go outside of the corridors. So essentially, my collaborators were like, no, we have to, we cannot deploy here. Well, 2 days later, my collaborators went back because I had to leave, so I had to come back, and they were like, they're going to try again. So they went there, there was no elephant, they started deploying, and in the afternoon, they heard a loud sound. By the time they looked back, like the cables were laid out, they were recording, they saw the cables and the instruments flying up into the air. There was an elephant running through, picked up the cable with one of its legs and destroyed. Basically, the instrument got destroyed. So anyway, we got some data that we could still go off of from other parts of the rift zone. Anyway, thank you very much for listening. That'll be all.
All right. Welcome, everybody. My name is Einat Lev, and I'm a volcanologist, so I study volcanoes here at Lamont. And I'll tell you a little bit about some of the really cool places that my research have taken me. So this is a map of the world. You recognize that. And all these triangles are volcanoes. So essentially, you can see volcanoes are a lot of places all around the world. Many are along the plate boundaries that Fola mentioned, but some are also in places like Hawaii or the Galapagos, just in the middle of a plate above a hot spot. Our trip will take us to Alaska first, then Costa Rica, move on to Spain, Hawaii, the Galapagos Island, Ecuador, and finish up in Iceland. So it's going to be a little bit of a whirlwind, but it's mostly pretty pictures. As for science questions, it's really straightforward. How can we tell when an eruption is coming? And when an eruption is starting and happening, how is it going to evolve? How can we study it? How far will the ash go? How fast will the lava move? And so on. So let's start with Alaska. This is research, part of a project called AVERT, Anticipating Volcanic Eruptions in Real Time, that was funded by the Moore Foundation. The goal was to go to this, whoops, whoa, that was sensitive, sorry. To go to the Aleutian Islands that are on a subduction zone plate boundary and look at these two volcanoes that are next to each other but behave very, very differently in terms of how they erupt and what they do before they erupt. One is called Okmok, whoops. Okmok right here, and this island of 4 mountains with the volcano active in the middle is called Cleveland. So I got to go to Okmok up here that had some big caldera-forming eruptions in the past and also some smaller eruptions that built some of those cones that are inside the caldera. Our project took the monitoring network that was before there, where everything was going on through radio links that were not working a lot of the time, to a more comprehensive. We added a lot of different types of instruments, and a lot of the data is now going through satellite, so that is a lot more reliable. It's huge, and there's no roads or anything on the island, so we went around in a helicopter, which was a lot of fun. And when you're in the helicopter, that's kind of how the view looks. Let's see if that plays the video. Not really. All right. That's how the volcanic terrain looks on the outside from the helicopter. There's a lot of streams and rivers and waterfalls, and it's absolutely pristine. And what we did was deploy some of these sites in stations, because we have to really protect it from the elements. The weather is really rough. This is one of the field engineers from the Alaska Volcano Observatory of the USGS. That's one of our sites. On the wall here, we put the solar panels, because that's how we power those stations. A lot of the times, the weather wasn't great, so we had to stay in the ranch house that we lived in for this couple of weeks. And, for example, did puzzles, because that's a great way to pass the time. Some days the weather was beautiful, and we're able to go outside and just look around and see, for example, these wild horses and the moose and the deer. So another part of it, after we finished in Alaska, was to go to some place that is a little bit more accessible, where we could also invite others in the community to help us and try different types of instruments. So we went to Costa Rica, where there's a volcano called Poas, right here. And this is the summit of Poas. It's all covered in ash from explosions and eruptions in the past. And these are the suburbs of San Jose, the capital of Costa Rica. And you see it's super close. So it's important to know when is it going to erupt, how is it going to erupt, and what's going to happen. This is the summit of Poas. There's often a volcanic lake that's super acidic and emits a lot of gas, sulfur. One of the things that AVERT did at Poas was to install a thermal camera, because the temperature of the water in that lake is one of the indicators that it might be getting ready to erupt. And you see that this is an observation deck. We see a lot of people that come and want to see that beautiful lake when visibility is good. And so that's why it's also super important to monitor it continuously. We installed the sites. The weather, again, wasn't always great. It was super rainy in November, and we had to carry all the equipment into the crater. But it was a fun adventure. And then one of the things that happened while we were there is, after a few months of just kind of gurgling quietly, there started explosions. And those explosions lasted for a few months. So we were taking this video, and it just started exploding behind us, which was really spectacular. Like I said, it was super rainy. It's one of our pictures in the mud. And behind us is one of our stations that included a seismometer to record earthquakes, a GPS sensor to sense how the ground is moving. Is the volcano inflating in the preparation for eruption? There's also a magnetometer that measures if there's any changes in the magnetic field underneath the volcano. So now we're moving from a situation of a subduction zone in like Alaska and Costa Rica to an ocean island. And this eruption that happened in 2021 in one of the Canary Islands, La Palma in Spain. Located right there. The eruption of Tahoe-Kaita volcano, it happened right on kind of the flank of the volcano, and very quickly lava flows came right down the mountain and covered many communities and fields, and destroyed the banana plantations that were there and the roads and everything. So that was a major disaster, billions of dollars of damage, and many lives upended. So we went there and we wanted to see, okay, this is an interesting eruption because it wasn't this huge explosion and it wasn't just a quiet oozing of lava. It was actually doing both at the same time. So we wanted to see, what can we see that would help us explain why it's happening at the same time? You see here there was a lot of ash that came out, and there was also all these lava flows that were going towards the coast, towards those people's houses. So we took a lot of pictures and a lot of videos. Sometimes it was very, very ashy. You couldn't see that much. And these are houses that are covered in ash right at the beginning of the eruption. We installed 2 permanent thermal video cameras on these 2 sites, and then there was kind of a traveling camera that went and recorded a lot of videos around. There's one of the sites looking directly at the eruption site. That's another site. It was on the roof of a person's house that got covered. These are pictures from cameras, and we look at both the temperature of the plume as well as we track particles in the video so we can see how fast it's coming up. So it's a measurement of the velocities. And then using that analysis and looking at the lava flow and how fast the lava flow is coming out, we came up with a diagram that there's this plumbing system that's inside the shallow part of the volcano, where sometimes the magma would go out as lava, sometimes it would go out as explosive ash, and explaining how that would happen. These are some pictures from the drone. We also use drones to look at the lava flows. And you can see here some destroyed structures as well. Again, the drones had both a video camera and a thermal camera. It's the combination that is super, super useful for looking at volcanic processes. So that combination of drones also helped us a lot in Hawaii at the 2018 eruption at Kilauea. Reminding Hawaii is this chain of islands in the middle of the Pacific Ocean. And in 2018, an eruption happened not at the summit as it used to be or close to the summit, but all the way down at the lower part of the rift zone, meaning those fissures where the magma is coming out were right in the middle of subdivisions and people's houses and fields. So for example, this is a town called Vacation Land near the coast. That is a before satellite image, and that's an after. This is the town where the vents actually opened, so that's a before. And that's how it looked after, with those vents right there. So this is supposed to be a video. Did it work? No. Sorry. Did I just leave? There you go. There you go. Okay, so to study the dynamics of the lava flows, which is a lot of what my research is about, it's really great to take videos with drones, and especially at night, because that's when you see a lot of the details of how it's moving. And this video could have shown that. That's a thermal video. You see the lava flows here. And here what happens is actually that lava flows went into the ocean, and that's a reaction. So there's a lot of toxic gases, a lot of tiny, tiny ash particles out of that reaction that went up in the air. Another chain of islands that is in the middle of the Pacific Ocean is the Galapagos, located right here, belongs to Ecuador. We went there again with our drones in 2018 to look at a recent eruption that happened right there. These are all fissures, the cracks where the magma came out, and it went down the slope. So lots and lots of lava flow areas. This is the bag where we took a big drone. Wasn't super comfortable, but did it. One of the things we looked at was a fusion of sulfur gases. So this is a tiny gas sensor that we put on top of our drone. That's a great site to look at sulfur coming out. Whoop. And that's a drone right there. An interesting thing about lava flows is they come in different types, different surfaces. So it would be really cool if we can map what kind of lava is where. But it's super annoying to walk on this, as you can imagine. So it'd be great if we could do it another way. So here is 2 types of lava, A'a and Pahoehoe, and we developed a method to look at the drone imagery and do a machine learning algorithm to automatically do that for us and say, this is an this is a hoi hoi. And then we can use these maps to say, at old flows, this is how fast they were moving and so on. In the Galapagos, we also had the fortune to interact with the park services and the public safety and discuss the kind of nature of that eruption and the response. So it's always really cool with volcano science that is super applied. You see right there that people are being affected from the finding of the research and the eruptions themselves. Lastly, I'm sure you've all heard about the eruption in Iceland that have been going on the last 3 years. So we went there again to look at the lava flows and how they happen. In 2021, we went to the very first one just after it started and collected some drone footage and images of how that vent started and collapsed and how that lava flows went. It was during COVID, there was no school, so I actually had the luck to take my daughter with me. And it was rainy and all that, but like, who cares, right? It was so magnificent. So looking at that, one of the exciting parts for me is, who I go to the field with, and that always makes a difference. So that was one of the funnest trips ever. So thank you. All right.
We have time for a few questions. My colleagues have microphones. Please use them.
Jake, come on. Thank you so much. So I had 3 questions, actually. One, how did you guys manage to get into such interesting field work? I have a little bit of an interest in field work. I'm more focused on lab work in terms of research, but I do want to have some aspect of that in my career. 2, in terms of the shifting of the tectonic plates, does climate change and global warming have any impact on how that works? And 3, what are the environmental impacts of volcanic eruptions? Those are the 3 questions on my mind right now.
So for the first question, in terms of getting into cool field work, volcanoes are cool, so it's kind of easy, just come to the field. But also, I think it's also important to remember that even though we get to go to really cool places, field work for me is a couple of weeks a year maybe, and the rest of the research is in the lab or in the computer. So as long as you're interested in the topic, that really is going to be more the most of your time. And then field work is just one of the tools of getting there. Plate tectonics, you guys?
Right. So I can add to that too. Getting into the field. So my master's degree involved a lot of geophysics and remote sensing work, studying rifts. But I learned so much, and I realized I really want to know more about how to interrogate structures in the field. And for my PhD, I targeted an advisor that knew how to integrate geophysics with field observations, and so that kind of helped me to get into the field. And for trying to remember your question about climate change interactions with clip-on. So this is one of the critical science questions right now that we're also trying to explore. But the easiest way to look at it is on short-term scale. So do we see any weird behavior in how faults are slipping in present day that can pinpoint or fingerprint influence of climate change? I would say right now we know that seasonal variations, seasonal variations in, say, lake levels, cycles of dry, wet, does impact how clamped faults are and how unclamped they are. So to get faults to slip, you want to unclamp a little bit so it can slip, because tectonic forces keep pushing on them, trying to make them slip. So we know that that happens seasonally anyway, and there are forecasts suggesting that if you have continuous drying of lakes around the world, in areas where we have active tectonics happening already, it can exacerbate frequency of reactivation of faults. So there's a potential there. And I must tell you that the recent New Jersey earthquake, all the stuff we've been doing here at Lamont is suggesting that there might be some influence on climatic changes, basically filling up of reservoirs in the area could have led to the triggering of the earthquake. So That's how I would answer the question.
I think on that too, certainly if you, I understand this much more from a volcanic perspective than a tectonic perspective, but if you lose ice, the ice has this enormous weight as it's pressing down on the Earth. And as that ice retreats, the Earth is actually rebounding and lifting up. And so in a way, it's a release of pressure. And so you can see this increase of volcanic activity where you have warmer periods or a reduction of ice. And so obviously that shifting of the Earth also will have some influence on tectonic behavior around those parts of large ice sheets. And then also, yeah, for me again, it was, I was looking for research projects that were affiliated with work in Antarctica, which was how I started working in this field. And all of the people I was reaching out to were doing field work and collecting samples, so that was how I got involved with the field component. But again, yeah, it's a small fraction of a lot of other time spent in the lab and at the desk. Yeah.
Hello, I have a question. It's more frivolous. I'm over here. Volcanoes. I've been to 2 volcanoes in my life, Kilauea and Mount St. Helens.
Yeah.
I'm probably going to go to the one in the national park in California soon, next year. What other volcanoes should I see?
It's like asking me what my favorite volcano is. I get that a lot. There's no answer to that.
Come to New Zealand.
Yeah.
Okay, it's not a bad idea.
Yeah, I think Iceland is spectacular because everything is so fresh and so new, and you know, you might have luck to see an eruption if conditions are right for visitors. I also think that volcanoes in Chile are spectacular because they're high up in altitude. They're all beautiful cones, just like in the cartoons.
Can people get there? I mean, is it...
Villarrica is a super popular tourist site, so you can go there. Yeah, the Galapagos are unbelievable. Yeah.
Thank you.
Everywhere, really. Sorry.
Give 3.
This might be a stupid question, but you know, on one of the maps that you had, it had the Pacific Plate and it went all the way down to South America. But I'm thinking, like, we usually think of the Ring of Fire like as North America. Is there activity in the Southern Hemisphere and we just don't hear about it around here?
There's tons.
But we just don't hear about it?
Yeah, I think we do hear about it because, say, Chile is the site of many major earthquakes. And sometimes when they have the really big ones, we sometimes hear about that. There's been a few really big eruptions, say about 8 years ago, 10 years ago in Chile, that also had this huge plumes and clouds, and some of the ash went over, across to Argentina. So you can, Chile is super active on that. Of course, Central America has a lot of volcanoes, a lot of earthquakes. Costa Rica, Nicaragua, all of these folks. Yeah, now it's like, oh yeah, yeah.
Any activity at Mount Baker or Mount Rainier?
Not that I know of. They're pretty quiet. Mount Rainier, the main concern is the lahars. There are layers of ash, non-consolidated ash, that are on the mountains, and they might be triggered by big rain or some snow melt that would then be a debris flow that goes down the valleys. That's the main concern. But there's monitoring on them, and if there is unrest, we'll know.
There's an uptick of earthquakes in Mount Adams, and although there's no indication of an eruption.
Where's that?
In
Washington.
In the Cascades.
Where? In Washington.
Northwest.
Wow.
Yeah.
All right. Well, thank you. Thank you.
Thank you.
All right.
Guys.